this juncture, unprecedented in the recent history, last 100 years of history of mankind, that it is science and technology and which will allow us to pick up the challenge by challenge from this pandemic. Issues, multiple problems, ranging from global issues to local issues, and where science and technology can play a major role. University in Assam, and for that matter, in the entire Northeast, except the IITs in Guwahati, expected, and people from the society look forward to the scientists, to the faculty, to the researchers of this university for solutions they encounter. We had problems of climate change, we had problems of health, the pandemic, and it is science and technology resolve these issues. While fundamental research in fundamental areas of science and technology is critical, requirements to undertake science, to undertake research in science, educational value. Over and above this, in the Northeast, which is one of the few biodiversity hotspots, and we have other advantages of being close proximity. Or there is a necessity for embarking upon research to value traditional knowledge that you have take it to the advantage of the people. Along with research in the applicational aspects, and finally, validation of the traditional knowledge are extreme importance whenever we talk about research in the domain of science and technology. And in this field, we have great confidence in Assam Science Technology University that they will provide good leadership, augmenting whatever research that has been going on, and we will soon have path-breaking researches findings from this university. This 3-day national conference has got an interesting array of subjects, right from physics, from astronomy, plasma physics, to even subjects like horticultural and immunology. And we look for scientists already established and younger ones, so that this 3-day national conference becomes a very successful one. I wish all great success, and my heartfelt thanks for being invited to this inaugural function. Thank you very much.
Thank you, Professor Buragmai, sir, for your kind presence in this conference hall today. I request our Honorable Vice Chancellor to felicitate. Now, I would like to request our most respected, the Chief Guest, Sir Chandrasekharan, The Professor Chandrasekharan does not require any introduction in the scientific world. Or Professor Emeritus of BITS Pilani, and he has been appointed as the chairperson and chancellor of Academy of Scientific and Innovation. I request the Honorable Chairman and the Chancellor, Professor Chandrasekharan, to give it. Sir, please.
Thank you. Distinguished guest, Professor Ashutosh Sharma, Vice Chancellor, Dr. Dheeraj Bora, guest of honor, Professor N.C. Talukdar, and Professor Alak Kumar Burgahan, distinguished invited speakers, oral presenters, and participants of NCRAST 2020. A very good morning to everybody. My special thanks to Professor Dheeraj Bora for giving me this opportunity to be a part of the inaugural ceremony of this conference. Well, fortunately, thanks to the internet technology, we can attend the conference in large numbers in times when, owing to raging pandemic COVID-19, we need to eschew gatherings and keep physical distance even otherwise. I must say I have never felt prouder of my own field of research, which is silicon chip design, design of computers, and electronic systems for networking and communications. Today I feel very proud of my field because this field has been so crucial in these trying times to keep our interactions, education, and commerce going. That kind of illustrates the power of technology, which is what this conference is all about. So I'm really happy that we have had in these recent times a demonstration of the power of technology to help us through very difficult times. Not just the information communication technology, but the technologies of based on biological sciences. It is amazing the speed at which vaccines are being developed. That has never been heard of. Equally amazing is the fact that vaccine candidates are being computationally tried through models on computers to reduce the time to figure out the proper target. So it's kind of very amazing that technology has come to the rescue of this society. And it is therefore very apt that in the northeastern region of the country, this very important conference is being organized, and that it actually covers several different fields. All fields are extremely important, but we have here some very, very important fields pertaining to fusion power. So there are global experts I was looking at. There are 10 invited talks by very distinguished international and national speakers in areas that span plasma physics pertaining to nuclear fusion power, high power radio frequency sources required therein, sustainable cities, biological sciences, which again, as I said, through this unusually fast pace of development of vaccines have demonstrated their utility and worth to this society. You have experts talking on immune system functioning, neuroscience, agriculture, particularly rice varieties that do not permit large accumulation of arsenic. So all these are extremely important subjects, and I think a conference where it brings various disciplines, so extremely important. Today, disciplines are no longer in silos. Disciplines interact with each other, they support each other, they draw from each other, and they contribute to each other. And this interdisciplinarity, multidisciplinarity, sometimes transdisciplinarity is becoming extremely important. Gone are the times when we could work in silos in our own narrow field and spend a lifetime doing it. For us as researchers to be relevant, we really need to look at how my field can contribute to something else in scientific research, which takes us further on the path of its application for the benefit of the society. So I must thank the organizers and must congratulate them for this very thoughtful exercise of having one conference which provides opportunities for international experts, national experts, practicing researchers, students to come together and share knowledge and information on this. I would like to convey my best wishes to the conference organizers for a very successful conference. And I would like to once again thank Professor Dheeraj Bora for giving me this opportunity to be here virtually this morning with all the experts and participants in this conference. So thank you very much.
Because of distance, probably will not be able to facilitate right now. And so our this symbol of love as a token of memento, I'll be saying.
Thank you.
May I request our distinguished guest, Professor Ashutosh Sharma, who is the Secretary of Government of India since 19. Professor Sharma, he is known to the scientific community as a outstanding scientist. And from that, he is a graduate from IIT Kanpur and later on educated from USA, University of New York and University of Pennsylvania. Number of awards in his credit from Government of India and elsewhere also. He has published numerous publications, I think over 350 nationally acclaimed journal, and filed over 15 patents and numerous invited lecture in the field of science. And his expertise is, of course, the multidisciplinary nature. And wide spectrum in the nanotechnology, thin polymer films, and nanocomposite, environment, functional interface, micro and nano machines of soft matter, nano, etc. And I request our most honorable distinguished guest of today's function for his Ancast 2020. Professor Sharma, sir.
Good morning. Namaskar to everyone. Can you hear me?
Yes.
Okay. Oh. No, that's fantastic. And thank you very much, Professor Dheeraj Bora, for inviting me to this very exciting conference, very forward-looking, conference and its contents and the speakers that we have today and going forward in the next days. So my namaskar to everyone who has gathered here. We have heard some visionary speakers here just now, Professor Chandrasekhar, Professor Talukdar, Professor Alak Kumar Burgoyne, and of course the Vice Chancellor, which attest to the importance of this conference. I'm very happy to note that the topic for conference is recent advances in science and technology. So it is not focused only on one particular narrow area of science and technology, but takes in its fold all the important things, all the exciting things that we all need to know as scientists, as technologists. And it was already pointed out by Professor Chandrasekhar that we no longer live in silos, that our science and technology is now becoming seamless. We may call it interdisciplinary, multidisciplinary, or out of discipline even. Um, the fact is that this whole concept of interdisciplinary and multidisciplinary itself is some kind of misunderstanding. It has been created because for the ease of undergraduate teaching, we first created disciplines. So which has meaning because we need to have an identity for the people who study to get a particular kind of job. But when we extrapolate this in the area of new knowledge creation, generation of new knowledge, the knowledge, in fact, the most useful knowledge, the knowledge at the frontier is in fact does not have discipline. It does not admit of discipline by very nature. So we must not extrapolate what we do for undergraduate teaching. We must not be confused about it, that this is the same thing that we can do for doing cutting edge research. Now, of course, this conference is about recent advances in science and technology. I may also add here that going forward in the future, we may also add increasingly the word innovation in it. There is a very good reason for it, that while we are all very intimately connected to knowledge generation, the consumption of knowledge which is produced is of equal importance. And that is signified by the word innovation. So you see, oftentimes, if I'm talking to my younger friends here who may be listening to us from somewhere, um, there's a clear distinction between invention and innovation. Oftentimes, these two terms are confused and people use them interchangeably. In fact, invention and innovation are orthogonal to each other, mathematically speaking. So they are, in fact, could even be independent of each other, and they are, in fact, 180-degree out of phase with each other. So invention can be defined as something for which we need resources. We convert resources to knowledge, new knowledge. And this is the primary job of universities, IITs, all the institutions that generate new knowledge. But at the same time, that knowledge has to be consumed in order to produce new resources and new opportunities, socioeconomic opportunities. So therefore, it is the invention and innovation working together that close the circle of knowledge, which brings in the concept of sustainability of knowledge in a society. And of course, now, there is more and more understanding and emphasis on innovation. Other words, when we produce our students, when we have a lot of young faculty, they could participate in this activity of converting knowledge into new resources. Whole lot of that is happening through startups. And so the startup culture has picked up really, really fast. For example, I'd be happy to share with you that just the Department of Science and Technology made more technology incubators in the last 5 years than in the previous 50 years put together. So today, for example, we have something close to 140 incubators spread over campuses, spread over many different places, so that there is an opportunity coming up really, really quickly for our students to make use of their knowledge. Uh, and that's very, very critical. I'm sure that all of us appreciate the value of using the knowledge. So there are two different processes at work. This is the push of knowledge coming from universities, R&D institutions, and there is also a pull of knowledge which is coming from startups, is coming from industry, it is coming from society at large. So an interface, a good interface between invention and innovation really is the need of the hour. Now, people talk about the future of science and technology. A very important direction of science and technology is becoming seamless, is the convergence of many streams of science and technology coming together in order to produce new technologies, to produce new exciting science, and to produce new products. An example of this convergence is what you may call the rise of intelligent machines, Industry 4.0, Internet of Things, the rise of data and cyber and digital in everything that we do. And it is thanks to that that we are here meeting today. Even though, oftentimes we said that Northeast has more geographical isolation because transport may not be as empowered as, for example, going to New York City. But you see, over time, these things would become less important, as indeed the conference today is already pointing out to us. In the good old days, maybe we had meetings and conferences attended by, few tens of people to few hundreds of people, or maybe even 1,000 people. But today, that's the norm. So every day I get to actually speak with, to interface with, to interact with few thousand people every day. And that would have been impossible just few months ago. So this is the new normal. It is about the convergence of digital cyber in every aspect of activity that we do. And so no matter what kind of scientist I am, I may be a chemist, I may be a physicist, a material scientist, a chemical engineer, a mechanical engineer, electronics, electrical, no matter who I am, I must pay attention to the convergence of new elements, the future, which is coming to us at faster and faster speed. The disruptive technologies, exponential technologies, and the example I gave, for example, is cyber physical systems. A cyber physical system is defined as the convergence of communication, of computing, of autonomous decision making based on the data and communication, based on the perception, which is in the form of sensors, and then converting all of that into autonomous action. So Industry 4.0, in fact, is completely based on this concept of the convergence of digital cyber data on one hand, and the physical machine, the mechanisms, the sensors, the actuators on the other. And this is going to be the forever future. As far as you can see in the future, it is going to be the growth of this sector, of this, in fact, the concept. So today we talk about Industry 4.0. How is it different from earlier industries? So we all know that Industry 0 was about muscle. It was about the movement of muscle and the control of muscle, the brute force. Industry 1 was about the steam power and centralized industry. Industry 2.0 was about the rise of electrical power and therefore a distributed power source and therefore machines getting into our homes and workspaces. Industry 4.30 is something that most of us have actually seen. This is the rise of digital, but the rise of digital, which is passive, which means that we are not integrated with that digital, that it is still in our hands. And basically, I manipulate that digital, and my brain and that digital and the machine in some ways are separated from each other. Industry 4.0 now is the convergence of all of that. And if you look at the future, the industry, the next generation industry and society would be based on finally also integrating the biological, the life, into this web of digital and physical. So the challenges of future are manifold, and these challenges should now get reflected in our education, in our research. There are new opportunities coming up. DST, for example, started a new mission called Cyber Physical Systems at an investment of nearly 4,000 crores. 25 hubs and spokes, 25 hubs in all areas of cyber physical are being established, have been established, and they will go forward with speed and scale. New technologies, disruptive technologies like quantum technologies are on the horizon. And we are in the process of setting up a national mission on quantum technologies at a cost of 8,000 crore rupees, about $1 billion, which in terms of purchase power parity translates more into like $3 billion. So we have to be fully ready for the future before it arrives here in terms of invention, in terms of technologies, in terms of innovation, in terms of human resources. And we are all actually participants in that process. We are creating the future now. So I urge all our participants to think about these things, that we need to think of doing science in a little different way. Our science can no longer be focused only on a very narrow silo of knowledge. It is not about it's not about tool-centric approach to science anymore. It is about problem-centric approach. The challenges of future, the challenges of today, just to name few, these are about health, transport, environment, energy, clean energy, of course, water, raw materials, resources, about climate, about, all of these. So these are actually problems which are multidimensional. The problem of water is not only problem of physical chemistry or organic chemistry or condensed matter physics or soft matter or mechanical engineering or chemical engineering or electronics or what have you. Actually, it requires a team of people working together in a cooperation mode rather than competition mode. So there are many conceptual changes which are needed in our doing science. You see, India is always very empowered now in terms of, let's say, number of scientific publications. The Nature Index last year put India in the third spot globally in terms of number of science and engineering publications. So what is our need? It is not only to scale up our numbers, but to scale up relevance and quality. So we must all emphasize with our students, with our research projects, the quality, which means that, new concepts, new insights, new applications, new inventions and innovations, not just being followers of the most recent fashions and trends, but for being leaders in the areas that we define. Many of these areas may be India-centric, or many science and technology concepts and ideas that make sense in certain societies. We cannot be blind to that. So we cannot also blindly copy everything that happens elsewhere, no matter how bewitching and no matter how exciting it might look on the surface. There are many examples of that. We don't have time for that. So anyway, now we are in the time passages of COVID-19. But even long after the virus disappears, even from the margins of history book, our challenges of science and technology will remain with us. And one of the overarching challenges is the sustainable development. There has never been a generation before us that lived under the twin constraints of environment and climate. Other words, constraints on our resources, constraints going forward in the future about how we have to use science and technology in a responsible way, while at the same time paying emphasis on development, which is very much needed. Certainly in India, we need to bring out people out of poverty. We need to have standards of living, health, and so on. And that's not possible without science and technology and development. So this is a huge challenge to balance our aspirations of sustainability and development. And this requires a huge insight into how we actually handle our science and technology, and certainly getting out of silos. So I would conclude here by now saying just one more thing, which is the call of our Honorable Prime Minister for at Atmanirbhar Bharat. And we have seen many elements of Atmanirbhar Bharat in science and technology operating in the times of COVID-19. Many examples, we all know about them. Just few months ago, we had no ventilators, no PPEs, no even N95 and 99 masks. They were all imported. Now, because of the shared purpose, because of a shared objectives, because of the urgency of the problem, our scientists, our engineers, our industry, our startups, our mentors, the whole different stakeholders of science, technology, and innovation came together very rapidly. And we have today the world-class design and manufacturing of ventilators. We can export actually. I have been the part of the process of this development, and therefore had insights into how it happened. And all of that is a very compelling model that we may wish to take forward even in the times of peace, not just when you have a life-threatening war, but even in the regular days, the new normal. And I'm sure that many of those elements will remain embedded in our way of doing things, in our ways of thinking about things. So to conclude about Atmanirbharta and vocal for local, there are also other elements of Atmanirbharta in science and technology. Science and technology is a chain of knowledge. So it starts from R&D, basic sciences in some cases, applied sciences in other cases, translational sciences, development of technology, development of human resources, development of startups, and then industry and society and market. All of this entire chain is required for Atmanirbhar Bharat. And in between comes things like design, things like prototyping, and so on. So unless each element of this chain is connected to the other, the Atmanirbhar Bharat is not only about manufacturing. Manufacturing is towards the end of this chain. We certainly need to connect with manufacturing. We certainly need to have a good direction from the beginning of the research. See, all of this is very hard to do. I am a professor myself. I am a scientist myself. I have spent 30 years doing teaching in IIT and so on, right? So I understand fully. I totally appreciate the difficulty of this vision. But each one of us, finally, as a stakeholder in science and technology, is responsible for this vision. And as educators, there are other cultural elements that we need to emphasize for at Atmanirbhar Bharat. And these elements I cannot emphasize enough. The first of these elements is Atma Vishwas, confidence that we can actually do it, that we can be leaders, not just followers. It is not the education and intelligence that we lack, it is the confidence. So as an educator, as a researcher, it is my duty to imbue this cultural dimension in everybody that I interact with. The second such dimension is Atma Samman and Atma Chintan. These three elements actually make up the cultural aspects of Atmanirbharta. And so while we don't enough pay attention to these elements, all through my life, I have found out that our PhD students, it is not the training, intelligence, brightness, and the preparation they lack. What they lack is things like, Atma Samman and Atma Vishwas. And we should take 10% time off actually to bring these elements in our education, in our research systems to the hilt. I cannot never overemphasize this aspect. I have had people coming to do PhD from very modest background, from little villages who did not know any English, who were not exposed to any ideas about research and so on. But by the time they come out, they are world leaders. They are established big industries at the technology startups at the cutting edge, hugely successful, right? And so these ideas about communication, about confidence, and so on, is something that we need to really, really emphasize. The time for it has come. It is not only about teaching, like I would say again, a very narrow subject, which is required, of course. But while we dig narrow and deeper, at the same time, we also have to spread out horizontally to bring in all of these elements. I overshot my time. I apologize. And I wish this conference all the very best going forward in the deliberations. And I'm sure that this would be hugely beneficial to everybody who participates. And my congratulations to the team that brought together this conference to all of us. Thank you again. Have a great day.
Professor Sharma sir, and thanks for your sharing your vision for so much. And sir will be sending our love symbol of Gamusa to you, since it is not. Now, may I request all the dignitary to inaugurate our book of abstracts. Participants here that we have received over 350 abstracts for this conference. This is a Vice Chancellor, sir. Sir. So the book of abstract, we have received over 350 abstract from the scientists, and we are trying to disseminate all this abstract to everyone who is participating in this conference. Thanks. As a customary, I, Dr. B.R. Phukan, convener of this conference and head of the Department of Energy Engineering, would thanks and sincere gratitude to our distinguished guest, Professor Sharma, and Professor Chandrasekharan, for their sparing their valuable time with us and blessing all the participant with their for Atmanirbhar Bharat. Thanks so much for your kind presence and sparing your valuable time for this conference. You will remain grateful to you, sir, Thanks for everything, your support, and to grow this university and this region. Thanks to our honorable guest of honor, Professor Anji Talukdar, Professor Alag Buragohai sir, acceptance of our request and also physically present here in our small seminar room to grace the occasions and encourage all the participants. Thank you so much. I extend my thanks to our Honorable Vice Chancellor, Professor Dheeraj Bora, who is the engineer, of course, in this university. And we work with him, and because of his visions, everything is becoming possible. Thank you, sir, for your support, your guidance, and your leadership. And I extend my thanks to all the officers of Assam Science and Technology University, Professor Dr. Nipen Das, and ASTU team. And I extend my thanks to Professor Bujor Barwa, who has been with us since the beginning of this university as a guardian. Thank you so much for your contributions and help to this university. I extend thanks to all the administrator officers associated with TechIPT of Ministry of Human Resource Development for funding this conference. I express my thanks to all the participants, all the dignitaries, invited speaker, the people who are directly and indirectly associated with this conference. Ladies and gentlemen, thanks to all. Now I will request to start the technical sessions because of this we have already passed our time, scheduled time. So I will request our Honorable Vice Chancellor, Professor Dheeraj Bora, to session the first technical sessions. It will continue. Professor Bora, sir.
Good morning to all of you once again. Now we start our technical sessions. Today we have the first technical session where we have one plenary talk and then one invited talk followed by 5 oral presentations. And probably before we start the oral presentations, we'll have a short break, which we are not having right now. So let me begin by introducing our first plenary speaker. I would say it's an honor and great happiness to introduce Professor Shrikant Tripathi, who we worked together in Institute of Plasma Research in the beginning of 2000. And then Professor Tripathi completed his PhD in plasma physics. He did an excellent experiment on helicon waves. Those days was not very popular in experimental fields. He did some initial work in that field before he left for US as a postdoctoral fellow in the California Institute of Technology, Pasadena, California. His areas of interest have been always laboratory plasma physics, which includes charged particle beams, plasma sources, heating, current driving toroidal plasmas, etc., etc. Now he has interest even in solar and heliospheric physics, in which he studies the eruptive processes you see in these uh, celestial objects. Not only that, wave instabilities, energy transport, etc., everything is being looked at in his group. Right now, he is working as a research physicist in physics and astronomy department of University of California, Los Angeles. Today, he'll be telling us, and the title of the talk is Bringing Space Down to Earth, Laboratory Studies of Solar and Heliospheric Phenomena. Let me tell you, he is a very exciting speaker. He's been figured in BBC quite a few times talking on solar events of many kinds. So we look forward to listen to Sri Krishna Tripathi. Tripathi, over to you.
Thank you very much. Hope everyone can hear me well. I hope everyone can hear me.
Yes.
Let me begin by thanking the organizing committee, especially Professor Bora, for giving me this opportunity to be almost like being back home. And I also thank him for teaching me, the initial lessons of laboratory plasma physics and all the cool stuff that we did those days. And again, I am very impressed with all the talks that have been organized here, which brings in diversity and also the interdisciplinary nature of science, which is going to be very critical to our future progress. So, further delay, let me share my slide. So, so I'm going to talk about bringing space down to Earth. And of course, if you're not working in this area of laboratory plasma astrophysics, it may sound confusing. How can you bring space down to Earth? Because most of the processes happening on space, they have very different spatial and temporal scales. And in laboratories, usually your size is much smaller. Even your biggest plasma device on the Earth is going to be much, much tiny compared to anything important happening in the space. So how does it work? So again, I like this topic and picked for this meeting because this is bringing multiple different fields. So it's bringing in space physics, laboratory plasma physics, and when you talk about the plasma, by definition, it's multidisciplinary. So if you're an engineer, you can be happy doing plasma physics. If you're a physicist, you're going to be happy. If you're a chemist, you're also going to be happy. So it brings in all your basic applications, basic physics application, and also if you're interested in mathematics and all the. So I just made it a little bit more like basic in the beginning. So first half is going to be more like introductory in nature, and I'll be mostly doing like storytelling of how this field is evolving and what are we looking in the future. And the next half will be going into more specific details of how things work. So there are lots of experts in plasma physics here, but in case you are not working in this field, so the plasma we talk about conductive assembly of charged particles, neutrals, and fields. And then you may find a classical definition of plasma, like if you read the book by Feng Chen, it defines what the collective behavior means and what we mean by this, what are different aspects of plasma physics. But here on the left, if you look into this parameter space, where on y-axis, what I'm plotting is temperature, and then x-axis is density, it covers a broad range in density and temperature. And of course, the things are going to work differently. And when it comes to solid, liquid, and gases, that's basically on your right bottom in the corner. That's the parameter space of those things. So now, if you're interested in lab astrophysics, then basically you're thinking about what kind of physics you can explore in the lab so that you can understand solar wind, you can understand interstellar space, nebulae, supernova, aurora, all these different plasmas. Okay. So now, as I emphasized, so now contemporary research in this area, it has space application to space, material science, applied physics, and all those different fields. So this is broadly talking about the plasma. So now, if we think about laboratory plasma astrophysics, so why do we study them? So the reason is because astrophysical processes, they cover a very wide range of scale and energetics, and that those are basically governed by dynamics of plasmas. So if you go back like 50, 60 years ago, then most of our astrophysics was done by taking pictures and looking at spectroscopy. And if you can't understand things, well, in those situations, you're thinking about turbulence and reconnection, you know those ideas. Only when you can't explain things. But as we make more progress, we do understand that almost all these systems they're embedded with rich plasma. And then there are phenomena like acceleration of charged particles, formation of stars, planets, accretion disk, dynamo, reconnection, turbulence, a large set of problems and large set of systems, they all have underlying plasma physics governing their dynamics. So now, you may consider this all to be of academic interest, right? So if you're just thinking about societal application, then why should we care about, for example, geomagnetic activity? We do care because sometimes very difficult to think about the future. Maybe if you are like 10, 20 years from now, then something like space weather will become more important, as we also have like more spacecraft going out in space. And to give one example, if you look into the geomagnetic activity, which is driven by explosive events on the sun, and you can look into, for example, economically, you can think about the insurance claims within the United States. And it turns out that there are like several $1 billion of the claims are made because those equipments like transformers and power lines, they're damaged every time you have strong geomagnetic activity. So it does have economic impact on the society. And then, of course, when you have astronauts venturing outside the spacecraft, outside the protection of our magnetosphere, then you worry about the energetic particles and the impact of radiation. So therefore, this area has very deep fundamental physics connected to it, but at the same time, it has application and it has impact on the society. So again, coming back to the question, so of how you study these large scale phenomena in a lab. So this is comes in the detail of this area of lab astrophysics because it facilitates studying the phenomena of extreme regions of parameter space in a control lab experiment. And I'll go more in detail on this particular aspect. So now about the storytelling. So this is area actually that Hans Alfvén himself was very interested in it, and he contributed a lot. And of course, when you are trying to push the frontier of science or technology, then the beginning you get pushed back. So in the beginning in 1937, when Alfvén told that if you have plasma pervading this universe, and when you have impulsive events, then they are supposed to carry electric currents, and they will be capable of generating this galactic magnetic field. And he has difficulty publishing those papers for decades, but then later on people agreed that, of course, this is what's happening in the universe. So now to emphasize the importance of lab experiment, in his Nature letter in 1951, this is what he wrote. Because those days people were skeptical of lab experiments and what you can learn from plasmas. So he says, my conclusion is that in many fields of geophysics, we should not attempt to go directly from our writing desk to cosmical phenomena. It is much better to call at the laboratory on our way out. If our theoretically derived results are found in the laboratory to be in error, there is little chance that they will be right when applied to the geophysical phenomena this stresses the importance of scale model experiments. So this is what I'm talking about, scale model experiments. For different processes, you have to devise different experiments to develop a better understanding. So now at the heart of this problem is basically similarity transformation. So how do you transform scales from space to the lab? And the initial work was done by Alphen and others during like 1940s and 1950s. But now we have much better ideas because now our computer models are much better developed. And also the theory, magnetohydrodynamic, all that development has contributed significantly. And I'll give you one example when I go in more detail on experiment that I'm working on at UCLA. So now this is the right time to talk about basic plasma science facility where I work at UCLA. So the objective of basic plasma science facility is to provide frontier level research devices at Los Angeles. And the idea is that if you want to really develop a really frontier level experiment, then it requires a lot of resources. And then you can't build these devices like almost every other city. So the idea is that if you build such a large device, and then you can have time devoted for local group of researchers, for example, me, but at the same time, at least 50% of the time is open to entire community of plasma physicists. And of course, preference may be given to people coming like within USA. So one can imagine, for example, if there was a plasma lab somewhere in India, so you devote 50% of the time for researchers coming from universities. And that has significant benefit, not just in education and outreach, but also in pushing your research frontier and also training next generation of scientists. So this facility is jointly funded by US Department of Energy and National Science Foundation. So I think user facilities such as basic plasma science facility, they provide synergy and facilitate interdisciplinary research and technological advancement. So this is the main device again, the large plasma device, which is a 25-meter long plasma device. And this has a modular design. There are almost like 95 magnets. And in fact, at one end now we can produce up to 1.4 Tesla magnetic field. And this can produce almost 60 centimeter diameter, 20-meter long plasma. And of course, all these devices are computer controlled. So you can generate straight magnetic field, you can generate multiple mirror, you can generate single mirror, you can have like a magnetic beach configuration. And almost every week, there's a new group coming to do different experiments. And one of the strengths of this device is the diagnostic. So this device has more than 500 ports now. And even though this plasma is so big, you can diagnose it with the millimeter precision. And you can see all these diagnostic probes sticking out. And you can also automate them overnight. So when you're not there, you can have almost these automated probes taking data for you. So this is a picture of plasma. So there's a lot of technology development to facilitate this facility. So now you can produce almost like 5 into 10 power 13 particles per centimeter cube density plasma, almost 15 to 20 EV. And this plasma is produced like almost every second. So it's like high rep rate device. Now, thinking about diagnosis, so of course you're always pushing your boundary. So when you think about technology development, it's not just for applied research, it also helps your basic research. And once you develop these capabilities, it goes back and forth. So it helps everyone. So here is an example of trying to measure magnetic field with like less than millimeter resolution. So for that, we can build these probes, and these are grown with MEMS technology. And these are like micrometer size probes that you can grow. And once you mount it on your robotics diagnostic system, then you can acquire data in 3D. So that's the benefit. And here are the example of research which is being done on this device. And it's not like everything included. And you can see starting from wave plasma studies to fast ion physics, to microwave, to even looking into coupling of antenna. Like if you have RF antenna, how it couples power to the plasma, and then what's the effect of seed, laser plumes, Whistler modes. And even people who are interested in condensed matter, they use plasma to look into processes such as topological waves. And these are topics where I think recently they got Nobel Prize in condensed matter physics. But these are basically at the boundary of condensed matter physics and plasma physics. So since there's not much time, I think I'll just pick two topics here. And these two topics actually I work on. So the fast ion physics relevant to space physics and magnetic fusion, and then also looking into these arch magnetized plasmas and their eruptive process. So this is a picture. So of course, the large plasma device is large and long, 25-meter long. And this was my first project when I came here. So I had to build this, it's almost like a neutral beam source on fusion devices. And to build this, I had to read papers from 60s. And of course, those days, all the good science was done those days. So you don't have to develop like fancy code. And what it does, it can generate a proton beam, at least 25 kV energy and 10 amp. So almost like 500 kilowatt range power. Now we have pushed it up to 500 kilowatt range. And now what you do is, this source will generate these intense protons or helium ions, and then you can inject in the magnetized plasmas. And then even though this is a large source, you can rotate it around this point. This is the pivot, and you can rotate it with the half-degree precision. So what that means, you can inject these energetic particles at an angle, and then that will make helical orbit, like shown here. So this is computation. So it will generate this helical orbit that will propagate downstream in the plasma, and then of course you will lose at other end. And now once you have this, it can help you understand physics of alpha particles in fusion devices. For example, how it couples with TAE, toroidal alpha and eigenmodes. At the same time, the feedback on charged particle can reveal the physics related to your cosmic ray scattering, why you see this anisotropy in cosmic rays that we always see. So this is the rich area. And one of the very basic fundamental wave in the plasma physics is the Alfvén wave. And I will give you just one example on how the Alfvén wave looks in the plasma when it gets excited by this beam. So of course, there's no antenna used in this experiment. All you have this quiescent charged particle beam, and then through collisionless interaction with the background plasma, it can make all the tiny fluctuations, microgauss range fluctuations, grow to up to 1 Gauss. And then it generates this intense wave. And this is the movie of Alfvén wave. I hope I can, let's see. This is a movie. Now you can see. So this is current density on the right side, and this is your wave vectors. You can see how complex it is. And this is extracting the perpendicular energy from your beam and then getting these modes destabilized. And similar waves are seen in fusion devices, but here you can take data with millimeter resolution. So this is about this fast ion research. So before I proceed, may I know how much time I have? Do I have like 15 minutes? I guess I will proceed here. So coming back to the second topic, which is about eruptions on the sun. So what we are seeing here is, this is a movie of the sun taken in X-ray. So this is like EUV X-ray range. And if you take a picture, and then this is a movie which was basically covering almost 3 weeks on the sun in 2003. So
Tripathi, you have 20 minutes, no problem.
Oh, okay. Okay, that's sufficient. I have trouble playing some of these movies here. That's what I am trying to. Let me give one more trial before I move on. some reason movies are not playing in the Zoom. Okay, now. So this is the movie of the sun taken in X-ray wavelength. Okay. And this is almost 18 days. And this was taken in 2003 around Halloween storms. So this is around the time when we celebrate Diwali in India. So if they give me chance, I'll call it Diwali storms of 2003. So as you know, the size of the sun is almost 109 Earth. So these are like huge structures. And now we understand that magnetic field plays very important role on the sun. So we have almost this magnetic carpet configuration on the sun. And all these explosions are basically the plasma confined in these magnetic field lines that are blowing up. The other way of explaining it is it's almost like thousands of mini tokamaks lost their confinement, and then you're just like blowing out plasma all over. But the energy scale is huge here. So now, again, thinking about terminology, all these dark things are called filament channel. They look dark because their temperature is around 5,800 degrees C, which is much cooler compared to million-degree hot coronal plasma. And you see all these tiny sparkles, these are explosions actually, and then energetic particle from the sun impacted the SOHO, EIT telescope on the SOHO, and then that's just the spark coming from the optics of that thing. So this is happening far away, so how does it affect us? So if you just look into the time evolution, how does things evolve on the sun, okay? So to see that, because sun has a layered structure, photosphere, chromosphere, solar corona. So if you want to look into photosphere, you need different instrument and you need optical filters and all of them. So just to give you one example of one event in 2000, now here on the top left corner, you see the picture of the sun, and you see this darkest part, that's where you have very strong magnetic field developing. And once you have that, you can see here the time is 16 UT. And then almost 2 hours later, if you take a picture in X-ray, then you see this brightening. They call these active regions. You see this local brightening. If you wait long enough and you block the sun and you see what's happening surrounding the sun, then you see this bright plasma cloud kind of expanding out. So this is what they call coronal mass ejection. And then of course, as time goes by, the structure grows bigger and bigger. And then at some point it impacts Earth. And I can't spend all the time explaining that. So let me show you this movie. This is just artist view. But now this is showing you where the sun is, and it's showing you a blob of plasma which is ejected and how it interacts with our Earth. So now you can see this is the sun here. And then you see this blob of plasma. Very soon you'll see it coming out. And then this is CME, or also in the form of solar wind. You can see this plasma kind of moving away from sun. And now in this picture, you see the Earth is here, and this is magnetosphere. This is day side, and this is the night side magnetosphere. So as we know that we are lucky that we have magnetosphere, because that's what protects us from these energetic particles. So now these CMAs, sometimes they move much, much faster than the speed of the background solar wind, and they can generate shock and then accelerate energetic particles. And those energetic particles can potentially destroy any spacecraft electronics which comes in the way. At the same time, if you're outside, you'll be bombarded with X-ray and high energy radiation. So that's why it's very important to predict when these things are going to happen. But even if you don't have a spacecraft outside our magnetosphere, once this plasma hits your magnetopause region here, then it gets deflected. And then you see it gets deflected in the tail region. And this is what happened. So right here, you probably saw these field lines kind of reconnecting. And once they reconnect, then all the plasma from the sun gets trapped there. And that plasma actually comes back here on the field line of Earth, and then they hit the pole region. And that's what drives aurora there. And actually in my background, this is what the aurora you see. And in my background, you can see the beautiful movie of aurora. So this is the typical view of Sun-Earth connection and how it works. So now the question is, now I'm going in more detail, like how do you study this process in the lab? So if you just look into these structures, so the basic block, fundamental building block of this solar structure is something like prominence structure. This is arch plasma, and it has a net current flowing along it, and there's a magnetic field. This is almost like a half of your tokamak, except that the plasma property changes significantly from one foot point here to the other foot point. So these are 2 foot points, and plasma property change significantly. So it turns out, like even well before our spacecraft era, modern times, we knew that these structures like prominences, they can remain stable on the sun from weeks up to months. And then within minutes, something happens and the whole structure erupts. So what's the trigger mechanism? Because if you can predict based on observations of the sun that this is the time when this structure is going to erupt, then you can probably do some kind of like space weather forecast. So that's why it's important to understand the eruption. And of course, on the sun, events are not controlled, so it becomes very difficult and challenging to figure out when the eruption is going to happen. So in my experiment, I call this arch magnetic flux rope, this structure here. So now the lab experiments can make significant contribution by acquiring good resolution data, because some of the trigger mechanisms, they happen at micro scale. And on the sun, that micro scale means smaller than 1 kilometer size, and there's no way you can gather any data in that kind of resolution. It's not available. So that's why you need to scale it and look into the lab, like how these trigger mechanisms are being generated on the sun. So now when you do that, so what are 3 specific? So these are 3 points I felt that are important. The first one is, since you want to study this process, in the lab, you have to create a structure which looks like prominence. So you have to create this arch plasma. Then the basic thing which drives the eruption is actually a multitude of forces that are in equilibrium prior to the eruption. So now the relative magnitude of those forces has to be same in your lab experiment. And then you come into the scaling of dimensionless parameters. These are 3 specific things that I'm looking into. So the boundary conditions, of course, the picture doesn't tell you where the field is. So this is the typical boundary condition on the sun. So you see the region of positive magnetic polarity and negative magnetic polarity separated by something called PIL, which is polarity inversion line. And then this blue colored thing is arch magnetic flux slope. That's what actually represents a prominence. And the region, so now you can imagine if this is like a tokamak and you have current running through it, there's a significant hoop force, which is the force trying to push it outward direction. So what keeps it in equilibrium is this black colored magnetic field, strapping field, which is equivalent to vertical field in tokamak. So when you then you have this current flowing through flux rope giving you J, and then this field gives you B, and then you have J cross B force, which is pushing it down. So basically your strapping field force, J cross B force, is in the inward direction, and your hoop force is in outward direction. And in equilibrium, what you expect is that outward force and inward force both are in balance. And if you create imbalance, that's when you expect this plasma to just blow out. All right, so these are 2 like takeaway messages from observation. So the takeaway message is that these structures are stable for many, something I call Alfvén transit times. Basically, the Alfvén wave, the time taken by Alfvén wave to propagate from one foot point to other foot point is Alfvén transit time, and it's stable for many Alfvén transit time. And when these structures erupt, then it can drive larger events such as CMEs. So please don't worry about all these equations. There are too many of them. So just look here. So So I looked into different forces. There's a hoop force, there's strapping force, there's pinch force, and this is the typical ratio on the sun. Based on models and observations, we can evaluate them. And in the experiment, I designed the experiment so that when you create the structure, you have almost in the same range. These forces are in the same range. So that's almost 2 jobs done. So you create a structure which looks like what's on the sun, and then the forces, relative magnitude of forces, is also relevant. Now, how does it work? How do you think that they scale? Because on the sun, the size of this structure is almost megameter. And in the lab, it's meters. So how does it work? So for that, actually, we find out that the dynamics of plasma on the sun is governed by MHD, magnetohydrodynamic. And this is basically where the MHD is. But most of the lab dynamics is not just limited by MHD, but it goes beyond that. So you keep an eye on other effects which may just appear in the lab experiment. And that's important because it tells you where you have to be careful in relating stuff and where you can feel free to relate dynamics from the lab to the space. So here, this is basically your dimensionless parameter, and only thing comes here is the Lundquist number. So as long as your Lundquist number, this term here is small, basically the same kind of dynamics that happens on the sun will happen in the lab experiment. So then you can make a table like I have here, and then you just list these dimensionless parameters. So as long as they are like smaller than unity, then you're in a good position. So here you can see on the sun is smaller than unity, in the lab is smaller than unity. And you can look into other terms, which is basically governing terms in this two fluid induction equation. So once you have gone through this, and the one point I wanted to make is that I'm not the only one doing these experiments. So there are other groups working on different aspects of this. But in my case, since I also work with my colleagues working on Parker, Solar Pro Plus, and NASA, so they provided feedback. So the experiment I'm working on is more modular in nature. And you can address different aspects of the solar dynamics. So this is how the experiment is arranged. Okay, so this is done in a large cylindrical vacuum chamber. It has multiple plasma sources. So this source provides a background plasma, and then this one produces your solar prominence like plasma. And these green lines are strapping field that's being generated here. So now thinking about building this source, it's really, really challenging because what I'm using here is lanthanum hexaboride. And then to make it emit electrons efficiently, you have to heat it close to 1800 degrees C. And now you may know that your stainless steel will melt at 1400 degrees C. So then it means if you want to design this source, you have to use refractory metals and all the complications that come in with this. But once you are done with this, it's very reliable and it provides a very good quality of the plasma. So now the typical sequence in the experiment is, so of course you pump down this chamber, you fill up with the gas that you want. You can use helium or nitrogen. Then you can turn on this background plasma. This gives you background magnetized plasma. And then you turn on the magnetic field. So these are electromagnets. You turn them on, then you produce Arts magnetic field. And at that point, you can apply voltage between these electrodes. So then you have current running through it. So now you got Arts field and you got Arts current, and both are almost in the same direction in the beginning. And then as the Hooke force builds up, it will try moving it out. And then strapping field will try pushing it in. And by playing with those two fields and currents, you can generate varieties of scenarios that may be relevant to prominence conditions on the sun. So let me, probably I'll be done in less than 10 minutes. So here is an example in the beginning. So once you create this plasma, you can make it really stable. Actually, in my experiment, I can make it stable for like days because the plasma source is so quiescent. But to trigger the eruption, I looked into what's happening on the sun. And one component that people think about is the flow coming from foot point. So in this case, to generate flow, those working on the lab. Yes.
You have 5 minutes more.
Okay. Okay. So those working on lab experiment, they know that it's quite challenging to generate flow in the lab. So what I used here is the infrared laser beam, which I fire on these put points, and that generates alphanic flow. And once you do that, then this drives instability. And then you can see this structure erupting. And once you have this plasma, then of course you can dig deeper. You can look into fluctuations, nature of fluctuations, what different modes are, and then how whether there's turbulence playing an important role or not. So you can dig deeper in all of that. So let me skip this. So I'll give you one example of fast wave here. So now what I'm showing you here is that this is showing you XT plane. So basically you're looking into plasma profile here. And then as time goes on, at this point where I label it unstable AMFR, this is where you drive the eruption by these laser pulses. And once that eruption happens, then you see these phase fronts, a beautiful wave. And of course, I went through checking the dispersion relation. It turns out these are magnetosonic waves. And they're really, really intense. So typical density fluctuation is 16%, magnetic field fluctuation is 20%. And it has a characteristic frequency, about 400 kilohertz. So now if you use the same kind of dispersion relation for solar case, I can predict whether these things happen or not. And then I can also dig deeper and look into their characteristics. So here I'm showing you one example of the same wave, exact same wave, which I'm calling it magnetosonic wave or fast wave, or the same wave which is used in fusion devices to heat the plasma as an auxiliary power source. Almost the same wave appears on the sun, and this movie shows that here. So this is the movie of the sun. You can see this is where the eruption happens. And here in the bottom panel, the blue and yellow basically show you the region of higher pressure and lower pressure. So these are the waves that are propagating away from your active region, and then it just wraps around the sun. So you can imagine the net energy associated or power associated with this wave is huge. So this is the one example. Now we can look into other aspects of it. For example, you can take a picture of this plasma and you can see how unstable it is, almost like what's happening in the sun. So in this example, it's generating a very intense jet which is coming towards us. That's why it looks like a blob there. And you see all kind of oscillations. These are like kink or global oscillation that people look into the sun. But once you reproduce these structures and these phenomena using probes, you can dig deeper and find out, what the energy partition, whether reconnection is happening or not, and all those questions can be answered once you have experiment working in this regime. To give you last example on the resolution, I talked about we can acquire high resolution data because you know that on the sun, we don't have any measurement of magnetic field in the solar corona. So once you have scaled here, in this experiment, I can take measurement with almost millimeter resolution. So if I don't tell you this kind of data looks like coming out of computer simulation, but it's not, it's directly measured with the plasma diagnostic in the lab experiment. So here I'm giving you, this is probably my last data slide, and then I will go to summary. So you can see all these hollow pink colored lines are basically the magnetic field here, which is trying to mimic the magnetic field geometry on the sun. And the dark lines are basically the current here. So now if you let this plasma go, what it does. Let me see if. Let me give one more try. All right. So you can look into, in 3D, you can look into how this current streamlines they evolve around. And now you see this eruption happening. And then also it generates a highly seared current streamline here. And after a while, you can see this will break apart and all the current streamline, they will follow the background field and you see this jet coming out. So this is your high resolution magnetic data that you can acquire. And of course, you can also use camera and then you can use your EUV diagnostics to look into more details of something like that. So this is just to show you the capability of what you can do in lab experiments. Now, let me go to my summary slide. So just to give you takeaway message, I think that lab plasma experiments can help answer outstanding questions in space and astrophysics by carefully scaling up dimensionless parameters. And then I already described what experiments we do at UCLA in the lab experiments and how they're relevant with eruptions on the sun. So now there are unique advantages of using lab experiments because they can capture all scales, they are reproducible, they're well diagnosed. However, they should be used synergistically with remote observation, numerical codes, and theoretical models. You can't make progress if you're just doing it just by yourself. So therefore, I think interdisciplinary interaction is going to be key if you want to boost the pace of progress in this area. So that's all I have to say. So if there are any questions, I am happy to answer. Thank you.
Thank you. Question. If anybody, any of the participants, yeah. So if you could, in 64, are there questions or they are just greetings? Are there any comments? You can click it. Taller, right. Okay. Okay, let's read this. I have two questions. When by the proton beam, does it affect the plasma parameters? And how that you have shown?
Okay, so I think I missed part of the question, but if I understood right, your question is, when you inject the beam, does it change plasma parameters? So if you just look into the Coulomb collision cross section for this beam in LAPD plasma, so for electrons, it's about 100 to 150 meter. It's like almost 6 times bigger the size of the device. And then other collision cross sections are even up to kilometers. So this beam is truly collisionless when it goes in the plasma. But then the way it actually dumps energy is by exciting these waves. So those waves are being generated through cyclotron resonance or Landau resonance process. And once those waves grow bigger, then in the next phase they damp and then they heat electrons. So I do see indication of electron heating in this, but I don't see significant increase in density.
Let me read it out for you. It says, why the Earth magnetosphere is not symmetric around Earth? Pinaki Paul wants to know that. I think it's a simple answer. Why don't you give that?
Yeah, it's a great question because we have solar wind coming from sun. So the solar wind from sun is pushing against the magnetic field of the Earth. So the head-on where it pushes, it produces your magnetopause, and then on the tail side, the solar wind is kind of sweeping those field lines away from it. So that's why it's asymmetric.
Another question to you from Kamal Talukdar is, what is the minimum temperature and maximum temperature for plasma to exist? It's a general question, I guess.
Yeah. It's let me probably, you can see this here. I mean, when it comes to like textbook definition of plasma, usually we try thinking about the ideal conditions, but some of, like here you can see it's like telling 10^2 to 10^9, but there's no upper limit probably for the temperature. There's a very broad range of the temperature. So you can have starting from ultra cold to even hotter than like 10^20 degrees centigrade, and you can still have plasma. But those plasmas are like very different from what we are used to seeing. For example, if you look into plasma at the core of a neutron star, that's very different kind of plasma that I'm thinking about. So there's no theoretical limit for the temperature, I think.
I saw Mike Walsh there, our diagnostic head of ITER. Do you have any question to ask Tripathi?
Hello, Dheeraj. Not for now. Thank you very
Hi.
much.
Okay.
Also, if anyone has question and they're not able to ask here, they can email me. I'll be more than happy to talk or reply through emails.
Yes. Okay. So if there are no more questions, I would like to thank Tripathi, keeping yourself awake. This probably midnight, close to midnight. And I know your habit is to work in the night, but for giving us these exciting, beautiful pictures as well as beautiful science you are doing. And we hope you will talks, what people will be presenting during this course of 3 days. And
Yes, yes.
next time you visit India, the university to come and excite the guys here. Thank you
Yes,
very much.
I would love to visit. And of course, I'll be attending other talks too, including on ITER, and the next talk I'll be listening. Thank you. So I'll stop sharing now.
Yes, thank you very much.
Thank you.
This is an announcement to all the participants and our next speaker, Professor. Take here a 10 minutes break, which we were to take before the party's talk, but we are taking it in local time will be probably 10:58. Okay, we just take a cup of tea for our guest. Professor Das, we request you to wait for 10 minutes.
Should I present now or I wait? Okay. I think there is a break now.
Yeah, I think there's 10-minute break right now. There's a break happening. So after 10 minutes, probably we can start. That's what I heard.
Unmute करो. Hello. So now come back. So do we have Professor Das around?
Yes, I'm there.
The next invited talk by Professor Jiban Jyoti Guwahati, and he will be talking on a proposal at CUPAC for Northeast region. Professor Das, as a professor working in the Department of Physics, Cotton University, Guwahati. Previously, he worked as physicist at National Superconducting Cyclotron Laboratory, US. From 2012, the postdoc fellow in UNIRIB Center of Excellence for Radioactive Ion Beam Studies, Oak Ridge, National 2012. He has also worked as a visiting scientist at Institute of Heavy Ion Research 1990 to 2008. Professor Das had worked as a scientist at Nuclear Science Center in Delhi. Professor Das, he has done his MSc from IIT Kanpur and his PhD from Delhi University. He has been awarded the Best Scientist Award, Nuclear Science Center, Delhi, in 2005. He has more than 70 publications in international referee journals in nuclear physics and about 30 articles in Indian journals. So I request now Professor Das to share his screen and start the talk. And we have about 35 minutes presentation. I would request if we can have 30 minutes presentation, then we could follow with 5 minutes for interaction. Thank you.
Okay. Good morning, and thank you for inviting for this presentation. So,
can you bring down your camera a little bit? We see only your forehead and a little bit of your specs.
Yeah, okay. So,
yes, that's perfect.
Today, so thank you to the organizers, and good morning, everybody. Also, thank you to the Share sir for introducing me. So today, actually, I am going to talk a little bit different in the sense it is a proposal we are submitting for the Northeast India to have a acceleration facility. So also this is basically a slightly different science than probably the first talk we have heard, but there are certain aspects, of course, which are very common. So anyway, I will try to talk about this as well as show some applications to the different fields this accelerator is going to have. So this is our collaborations. It's a large collaborations we have from the all northeastern states. 7 states have joined together. We still haven't had a participant from Sikkim, which we are trying to collect. So this will go as a northeastern proposal. And then, so this is what we organized this workshop recently to formally the collaboration. So, and there we discussed then that how this accelerator will go. So I will kind of try to tell the basic reasons. Of course, the fundamental motivation is that I worked with accelerators, and when I was a student, actually, we used to think that we don't have any accelerator, and our seniors didn't do much. So, and because particle accelerators are really, we'll see how it is one of the most frontiers of modern science, and it opens up. But I think we cannot do that again. So I thought now I am senior enough, and probably we should come back here and try to put up something. And then, of course, I think we want to do a state-of-the-art accelerator facility. And but the basic and aim is that also we want people to get hands-on training. This is what I say. For example, we have IIT set up here or central universities. We essentially produce students, and maybe some local people get jobs. But fundamentally, I want to say that we need people who can do things by hand.
Hello, Professor Das. Professor Das.
And that is what.
Hello, Professor Das. Are you sharing your slides?
Yeah, I am sharing.
Are you sharing?
Yes.
You have to share the screen. We don't see anything.
I don't see it either. I do not see it either.
Yeah. Can you see?
Yeah.
Now?
Okay. Now it's fine.
Okay. Yeah. Okay. Then sorry. My apologies. Actually, I shared it maybe when I probably Zoom does not bring it back. I use Google Meet, so kind of this is a little different then. Okay. So I will repeat again what I have done. Okay. Okay. So today I am going to talk about this. Also, this thing at the side. Is it screen is fully visible, or it is getting cut by the side?
Looks good to me.
Please go ahead.
Yeah. So we are essentially forming an accelerator facility proposal we are submitting, and we want to, for that at Cotton University we are doing this Cotton University Particle Accelerator Center. So we want to propose this facility, and then so we have formed a collaboration from Northeast, and so that is what we are going to I talk today. And this is the collaboration. It involves all the 7 states of Northeast right now, and we are trying to get also Sikkim involved in this. So this is the basic part of it. So this is what we recently have a first collaboration meeting and discuss how to go about it. And so this was the slide for that. Anyway, let me now talk about what is the fundamental motivation. Essentially, we want to train students. I think the first thing is that we want to have our students trained in this modern science as well as doing hands-on things. I mean, this is a little different than setting up an IIT or a university or some research labs. But accelerator technologies, actually there is a huge amount of things you do hand, and these are very modern technologies, and I'll give some examples. And basic aim is that we want to give our students this training and also have their opportunity to do modern science. And then this is we'll see that how do we want to have that. I think this is what we want to make ourselves different from many national labs or facilities. And then of course this is the accelerator physicists and researchers. And hardly, of course, I will show you the way we are proposing the accelerator. We will do science, which currently is not is very unique to India in national perspective, and in some respect even in the world. So that is the basic our fundamental motivation. And then, but of course, particle accelerators, this slide is from American Physical Society journals. So you can see it is actually, particle is a tool of discovery actually, these accelerators. You can see they have 25 Nobel Prizes in physics, 22 in chemistry. So no other field has produced as many Nobel laureates in any particular class of instrumentation. So you can see, so it has a lot of very complicated and innovative things are involved, and that is where we want to work on this. And it is not like doing experiment in CERN or some other place, because it is only one aspect you learn. But when you actually have a machine and operate yourself, there is a very different class of experience and expertise one gains, and that is our fundamental goal. So now, the accelerator we are proposing is a electron accelerator with ECR ion source, electron cyclotron resonance ion source. This accelerator will be, of course, first of its kind in India, is the highest luminosity of the nation, and it will give unique beams, which are also not there. Not only the luminosity, also in some areas you will give beams, which currently researchers don't have in India. We are proposing to have 8 beam lines for experiments here in the name of 8 states. It will be given like Arunachal beam line, Assam beam line, Manipur beam line. I put everything in alphabetically. And then Sikkim, of course, I put a star because we have not yet formally joined the collaboration yet, but I hope we will be able to have it pretty soon. And then, of course, in the very long project, I will show you some time scale. In the first phase, we want to develop a PIMS facility for archaeology and geological research. This is essentially a carbon dating technology, the state-of-the-art carbon dating technology, and then it will be more efficient than anything that is available in the nation now, as well as more sensitive. So, and it will be, of course, first of its kind again in India. So this is the very first phase we want to develop for this facility. So let us talk about the accelerator now. So why our kind of accelerator is that we are talking about? The first such, actually this concept was invented at the Japanese Atomic Research Institute in 2011. So they have what is called a tandem accelerator. So I don't know if people are aware, but so I'll briefly tell. So this is actually essentially called a high voltage. So where we keep at this region where the ions get accelerated, this is typically 20 million volt. This accelerator runs. So what we do here, we have negative ions here. The negative ions then made vertical, and so this is a positive terminal. So this gets energy. So this will come with a -1 charge state. So it gets 20 MeV energy, for example, here, and then there is stripper here. So at 20 MeV, when you make this beam pass through a very thin carbon foil, it loses the electrons. For example, carbon beam you are talking about, you have carbon minus, which is 7 electrons now. That is how we have produced it. So carbon minus has gone up. So here, so it is in the stripper, you take out all the 7 electrons. So it will become 6 plus. Then you bend with a magnet, and because this thing is positive potential now, because it is a positive charge now, so it will repel again. But here now 6 into 20, 120 MeV you will gain because charge state is 6 now. So the same potential you have used twice. You have used minus charge state, so one you have got the 20 million volt, then you made it plus 6, and then you bend it, and then get 6 into 120, 6 into 20 is 120 million volt. So you can get a lot of energy like this. But this is called tandem accelerator. India has several of them at Tata Institute of Fundamental Research in Bombay and in Nuclear Science Center in Delhi, where I used to work before. But all those accelerators like this suffer a very serious problem, because one thing is that this stripper cannot take very high current. It breaks down. So the beam intensity you can get is limited by one aspect is that. So you get much less current. Second aspect is when you try to make a negative ion, you are adding extra carbon, you can add. So because that cell is not complete, you can add an electron, you can get 7 electrons. But if it's a neon or helium or argon, so they cannot take an extra electron because those cells are filled. So those beams are not available. So both all these Indian major accelerator facilities cannot give those noble gas beams, as well as beam intensity is low because of this stripper problem. So this Japanese institute has proposed this new technology. It is a very it's called nanogun. It's like a nanoscale, very small ECR ion source, but it's very highly efficient. So these ion source directly give the positive ions to thousands and hundreds of thousands of times more luminosity. And then those are now accelerated here. And you have a direct control on the charge state because this you can tune the field to get the charge that you want. So you can get high charge state, like what we have done for the stripper here. You can directly get from the ion source. You can get very high current. And so as a whole, you directly inject positive ion. So all this part is now not used. You can get high current and high beam energy. So this is the technology. And that is what we are trying. So we are now going to propose to build this accelerator for our center. So this is I am showing. So this is essentially the top part. So how it looks like. So this is the ion source, ECR ion source, the nanogun ion source, and then it bands with the injector, and then this will essentially give beam to the accelerator. So yeah, but I don't want to go to detail. I just want to give the concept. But here I want to show the proposition we are saying that this will be unique in India. So to make that point clear, I have made this two-dimensional plot. So in the x-axis, I am showing the beam particle current, or you can say the luminosity, or you can say the fluence available from the accelerator. On the y-axis, I am showing the energy that is available from the accelerator. Because when you do an experiment, you both about how much beam current you are getting and how much energy you are getting. So both the two national facilities at TIFR and Inter-University Accelerator Center, now it is called Nuclear Science Center, are in this region. You can see the maximum current is something like it's a 0.1. Practically microampere, so it's about 100 nanoampere. So this is slightly less than that. And this energy range, something like 10 MeV to say about 500, 600 MeV, you can get energy. So this is the range that covered by that machine. But there are not really experiments which need a huge current. So DST has done two mega science projects, one at Prayagraj, one at Kurukshetra, to essentially to extend this axis, the current level, because you cannot do a lot of experiments with such low current. So this is what the DST's mega science project, two facilities have come up in the last plan, that this essentially gives all the way up from, so instead of 0.1, you can get 1,000. So it's like 10,000 times higher current. So these facilities are, these are now commissioned as the DST's mega science project. And you can but see the energy is about say 1, 2, 3, 4 MeV or so. So in this range, they give beam, but their current is limited to this range. This opened up a new dimension of physics, especially at material modification and research. But it also left a lot of things which cannot be done. This, our new accelerator, we are proposing is this yellow region. So it's going to give current on the whole region. You can vary it and get for species in this range. But also you can see the energy that you can get a whole lot of energies. So we'll fill up with this new region, the experiment which is not there in the country right now. And I will show some examples of the competitive research, or not even leading research we can do with this facility in this energy and mass region. So let me talk about the science then. So I told that these are a unique region in terms of the energy and intensity. So what is the unique science? So investigating on the fundamental thing we want to do is the thermonuclear reactions rates in stars. That is what we want to measure. With this accelerator, we will be able to explore the universe. Just few minutes, couple of minutes after the Big Bang, all the nucleosynthesis started, how elements are formed, like oxygen 16 or whatever we saw on the Earth, how those are formed. So those we will be able to investigate because of this high luminosity and the energy range we are talking about. So this is one of the fundamental contribution we should be able to make in this science. Then I will also talk about basic and applied science in the neutron science. We are going to talk about accelerator-driven boron neutron tensor therapy. It's called BNCT, ADBNCT. So I will explain that example. The nuclear material and nanoscience, I think will be unique there because again, in this region, because DST, this is essentially for nanoscience and all, but again, you can see this is a limited range of energy and current. And this IUAC is one of the pioneers of India in this nanoscience and swift heavy handling materials, but you can see that intensity is too low. I'll see just what world is doing. And of course, finally, our phase 1, I will talk a little bit more detail, the PIMS facility for archaeology and geological studies. So, let us first give the example of the applied science. So I'm talking about here accelerator-driven boron science, boron cancer therapy. How does it work? Essentially, this is a new technology that is developed for cancer therapy, and its first clinical trial is in progress in Germany. So, and it is of course not there in India. So let me see how it works. So what actually happens is that boron is a compound. If you heat with neutron, it breaks up into a helium and a lithium. So this Q value is about a couple of MeVs, 2 or 3 MeV. So you can see roughly equal mass. If you think like that, it will be same energy. So it will be, of course, helium will have little more, but you can say that about 3 MeV. So it's about 1.5 MeV this will get. Now the range of this radiation that is produced, the helium and the lithium, is about 1 micron, and that is typical cell diameter. So the energy 3 MeV would be lost in a micron. So this the number we call it LET, linear energy transfer, is about MeV per micron. So there is a huge lethal dose, and it will kill the cancer cell immediately. So this is the basic nuclear physics of it. And how does it essentially work is that you inject a patient with a drug which has boron. Human body doesn't have boron, which is of course safe to inject. So such drugs are developed. So you inject the patient with that drug, and then you also make it some compound which is selective, only that is attached to the cancer cells. In this, you can say these are cancer cells. These are normal cells, and these green ones are the cancer cells. So if you can develop the drug that inject the patient with boron, which only absorbs by the cancer cell and does not absorb by the neighboring cell, then what happens if you put neutron on these cells? Now essentially you can see neutron only reacts if there is a boron. So you can see it will react only with these borons. And as I said, the linear energy transfer, that is about MeV per micron, is getting deposited in these cells. Because the range of this helium and the lithium are only a cell, so it will not go to the next cell. It will just kill this cell. So healthy cells will not be affected. But this is so lethal, it will kill all the cells with cancer. And this linear energy transfer we are talking about, it is about order of magnitude higher than currently proton therapy or the gamma therapy, the kind of dose that is required that patient has to go through. So it is much more lethal. And second thing, those radiation is indiscriminate. It is on the trajectory of it, whatever healthy cells are there, they will destroy all of them. But in this case, only because of this particular properties of the neutron interacting only with boron with a very high cross section, other things it doesn't interact much. So it will only produce in these cells and kill those. And so you can see that after that, it killed all those neutron cells, cancer cells, and these healthy cells remain. And so also neutron is very highly penetrating, and it can be used to do very difficult cancer treatment, which currently cannot be done. Like you cannot surgical or do something removed. Things like surgery and then therapy and chemotherapy mixer and all. But here you use single shot treatment actually. So because of this is it's highly promising and social applications. So this is what we want to do now. And okay, I don't want to go to the detail. And this is of course the first clinical trial that is progressing in Germany. It started in 2009. You can see this article in that it is a recent Science article last year. So in that, it was so that they are doing this. I mean, this machine is different to the accelerator, but we will have a different one. But okay. So essentially, we want to develop this technology, and it will be India's first. Next, I want to talk about something basic science. This is personally I do, is the star reaction. So essentially, you have previous speaker has talked about the plasma or the neutron stars inside what happens. So we are going to study here after the Big Bang, a couple of minutes after, when the elements have started forming. Many of those rays are still not known, and they are very important to understand. I will show some examples. But basically, the fundamental difficulty, I think it is better to understand that way, in measuring those reactions, is that those reactions are extremely low cross section. And we detect the gamma. So the photons that come out of the reaction, showing that this reaction has happened. So that is the problem. That is a very extremely low cross section. So you need very high luminosity accelerator. But also, because we detect with photons and the cross section is low, those photons are those photons are very small. So on Earth's surface, the cosmic ray, there is a you cannot actually do most of the experiments because the cosmic ray background is millions of times larger than the, the signal that comes from the reaction. So most of these experiments are essentially done deep underground. So I try to develop this whole field is called nuclear astrophysics. So in 3 kinds of facilities, the astrophysics over the Earth surface. So such things are of course still being done but there's a deep underground. The world leadership is now with LUNA, Laboratory for Undergraduate Nuclear Astrophysics in Italy. And so there most of the pioneering works are getting done. It's about 3 miles below Earth. This accelerator and the facilities are set up. And now new ones are coming up in China and US. And over the Earth, of course, one facility is DAE setting up at Calcutta, the Institute of Nuclear Physics. So, but such dozens are there. So, but anyway, we believe that this is kind of the leadership. But there's an alternative technique. We want to do it called inverse kinematics. Essentially, what does it mean to picture in your mind is what is that will make a reaction happen in the lab. But if we can make a reaction happen and then detect the photon in fast coincidence with the corresponding say helium Trojan which proton and give lithium 5 or deuteron lithium 6 or something like that. So what I am saying, that will give a gamma ray, will detect a gamma ray, also will get the lithium 6 in fast coincidence. If you can do both together, then of course you can see it will reject the cosmic. This is the basic principle we want to apply, and with this accelerator we will be able to do this. And essentially these reactions happen what is called a GAMO peak. It's a very small energy peak, and these accelerators we should be able to actually reach this energy at low energy to do this. So low energy and high intensity. So this is required for astrophysics reaction plus the background reduction, which you will do by doing coincidence. And such things are of course not done in India, and even worldwide. This is only one place this is done. It needs a supersonic Z target and special instrument called recoil mass spectrometer for inverse kinematics. And actually, I have worked for last 10 years in those 2 fields. So I kind of believe that this is what we want to do now. But so I just want to show how the underground research is done. So this is I am showing the slide from the LUNA that in Italy. It is a publication in 2020, 19. Last year it has come out. Their research. So they first had a 50 kV accelerator, then the 400 kV, and now they are upgrading it to 3 MV accelerator. So this is the new experiment and new accelerator. So they essentially do all these 3 accelerators they use and do the experiments, which is required to be done deep underground. So to take out the background, as I say, but this is like they do. But I think let us talk about the science. So So these experiments are very, of course, low cross section and difficult.
Das, 3 minutes.
For 5 years, they have taken 5 experiments to be done from 2020. This year, I don't know if it started this year or not, maybe next year it will start. So each year, they will do 5 experiments. 1 experiment each year for next 5 years. So these are kind of, say, understanding how oxygen is formed. It's very important. Still, we don't have precision data on that. And this experiment has to be done at 30 kilovolt. Similarly, this is for AGB stars, how it is formed, asymptotic giant branch, is involved 22 neon beam on alpha capture. So like these are the reactions that will be done. And our aim is to do this. They will do it, of course, proton beam on 14 nitrogen. So essentially they cannot detect, so they detect a gamma ray directly, and because underground they will not have background. But we will do the other way. We'll use the 14 nitrogen on the proton. That is why we call by the inverse kinematics. And then, of course, what happens, this 15 oxygen that is formed, because the momentum is conserved, this K is the beam momentum, so it will have a much higher kinetic energy so that we can detect it in a spectrometer. And we will use the supersonic jet target, which is essentially having proton target. So we will have these experiments. That is the way we will do. It is first such things is, of course, done at the Notre Dame, University of Notre Dame, but as you can see, we will have enough things to do ourselves because these experiments are so time consuming, nobody can exhaust it. And the first such facility has actually come up in Notre Dame. I think it has started commissioning. So anyway, our strategy, of course, is to compete with Luna. We want to do each of the experiment in the inverse kinematics and get independent set. So that is, I want to talk about nuclear astrophysics. Then I am talking about Swift-Hebbian in materials and engineering, in material engineering research. Essentially, I will try to briefly talk about why we need this accelerator, and then talk about Rutherford backscattering and ERDA, electrical detection technique, or online transmission electron microscope. So let me show that. Yeah. So this is just, I am showing European Center of Excellence, is Joint Accelerator for Nanoscience and Nuclear Simulations. This is a Center of Excellence, and that is where they essentially use the kind of machines we are developing. This is the first facility to use such machines. And they
Professor Das.
Huh?
Hello. Professor Das.
Yeah. Is it over?
Yeah, you have 2 minutes more.
Okay, good.
2 minutes more, please.
And so
wind it up so that we have questions to ask.
Facility, they are going to talk about do experiments, and this is the DST mega science. Part of it they are doing, the low energy part, but we will be able to do the major part of this research. And now finally, I want to talk about our PIMS facility. So essentially PIMS is a positive ion mass spectroscopy. So this is a radiocarbon dating with unprecedented efficiency and sensitivity. And that is what we want to do. It will be first in India. Typically, it is done by using accelerator mass spectroscopy, but that is more expensive and difficult. Less efficient. So this can handle several times more sample. So how it works is the 14 carbon is a 1 part in billion. It is there. So that is essentially hugely overtaken by the nitrogen 14 and carbon is to molecule.
Professor Das.
Yeah.
Please, can we wind it up?
Yeah.
We have questions also after this.
So this is what essentially PIMS we are going to do here. So 14 carbon will essentially here we got a different technology. So I'll just show in this slide the 14 carbon we get from the ECR source, and there we make a negative ion. So that 14 carbon makes negative ion, 14 nitrogen does not make. And then we can show that simply a Sarsgaard selector will take out the 14 carbon, and that way we can do very accurate dating, carbon dating, and that is what we want to propose to build up in our first stage. And also this accelerator, this uses the ion source, which is same as our accelerator, so we'll train our students in that. So I think, this is the whole the facility will look like, and we have got users who want to do this research of samples they have collected from excavation from archaeology. And then, so I think that is what I want to show. And this is where you can see kind of the first phase we are talking about 3 years of running of construction and 5 years of operation. And this is the kind of budget we are proposing for this accelerator. And then, yeah, I think I don't have to show that. And this is our land. And yeah, see some people who works together. So our land and everything, we are kind of serving our land. Well, actually, thank you. I think, sorry, it took a little long. I think the initial got a little off, but my apologies. Yeah, just repeating the few slides. Yeah. Thank you again. Yeah.
Thank you. Here is the first one. That is, sir, what should be the flux of neutron?
Okay. Flux of neutron, you can
Process.
see, yeah. We are kind of talking about a flux of the order of per solid angle 10 to the power 8
Okay.
per millistadian. And
one more question is that,
and we can of course get order up to 10 to the power 9. In fact, they are 10 to the power 9 to 10 to the power 10 with some. These are we are talking about a monochromatic part of the neutron beams, but we can get up to 10 to the power 10, which we are not doing monochromatic.
Yes. Next question is, what will be the energy of the neutrons that will be emitted?
Yeah, okay. So this is the first.
How will you shield the neutrons as it is a biological hazard?
0.1 to 0.65 and all the way up to 20 MeV you will get 20.6 MeV neutrons. This is the range of the energy of the neutrons. These are monochromatic neutrons we are talking about. Of course, 8 MeV to 14 MeV, these will not be monochromatic, they will be quasi-monochromatic. So this is the first column. It says, give you the energy of the neutrons.
I'm interested in this project. My question, can heavy, I think.
Yeah, I can hear your question, yeah.
Beam will be available according to said proposal or Linux facility. What about radioactive ion beam? What is the current status?
Okay, radioactive ion beam actually, we are of course, this will be a stable beam facility. This is not radioactive beam facility, but yeah, Delhi, the India's first radioactive ion beam actually I made. That is how I got the Best Scientist Award. So there we have made 7 beryllium, and then there are many other beams are possible for nuclear astrophysics. So if you have any specific nuclear radioactive ion beam experiment, we can discuss, because I was the principal investigator of that project also. So we can work together and do experiments for astrophysics or nuclear research. Yeah, that could be running very soon. It is an operating facility.
Okay, so if there are no questions, thank you very much for.
You're welcome.
Thank you, Professor Das, once again.
Time more than allotted. Yeah.
So you could maybe disconnect the screen.
Yeah.
Now we have 5 oral presentation. First one is by Manjit Kaur, who is at present in the Department of Physics and Astronomy, University of California, Irvine. Manjit will be speaking on transition from a dust field to a hollow vortex in a driven dissipative system. Manjit, can you hear us?
Yes, I do.
Okay.
Thank you so much for the introduction. It is so good to see you.
Yes, nice to hear you. Let's hear this nice picture. I'm seeing it after a long time.
Thank you.
Okay, we give you 15 minutes, maybe 12 minutes for the presentation with 3 minutes question answers.
Okay, thank you. Good morning, everyone. Yeah, so I am working in the University of California, Irvine. But the work which I'm going to show you here was carried out when I was a PhD student at the Institute for Plasma Research. Before I start my talk, I would like to thank the organizers, Bharat, Professor Bora, and others, to give me this opportunity to present my work in this diverse conference. um, so this is the outline of my talk. I will start with a brief introduction to dusty plasmas, followed by the motivation behind these studies. After that, I will show you an experimental setup which we had used for carrying out these studies. And then I'll show you results regarding this transition from filled dust vortex to hollow vortices. And at the end, I will summarize my talk. So dusty plasmas are low temperature plasmas mostly, where in addition to electrons, ions, and neutrals, we also have micron-sized dust particles, which get negatively charged, and the charge varies from 10 to the power 3 electrons to 10 to the power 5 electrons, something like that. And because of these high charges on each dust particle, they interact very strongly with each other, and also with their surroundings, and give rise to many new phenomena such as low frequency waves, their structures, rotation, etc. Now, because of the big size of these particles, they are very heavy, and hence they have very low mobility that present an advantage of direct imaging. These particles can be easily illuminated using very low power lasers and can be captured using any simple camera that gives us an opportunity to measure their positions and velocities very accurately. Vortices, we see vortices in nature. There are several examples, for example, smoke rings, whirlpools, Saturns, hexagon, etc. In these cases, we actually cannot control these vortices because these are like huge systems such as Saturn's hexagon. But if we can generate these vortices in laboratory, we can easily control them, and we can understand them better. For example, in dusty plasmas, we can generate these vortices and we can study their dynamics. Their dynamics can be analyzed easily because we can measure their positions and other things. So we can understand them in greater details, and because the main reason is because we can trace each and every particle participating in the vortex. So with that, this is the experimental setup which we had used. So the experiments were conducted in a stainless steel cylinder of diameter 31 centimeter and length around 50 centimeters. We used a green laser to illuminate the dust particles, and this green laser was aligned along Y direction. The illuminated dust particles over here were captured using a camera, which is looking at the dust particles in the X direction, and Z was our vertical direction. So these are the electrodes which are located right at the center. The upper electrode is a live anode of diameter 9 centimeters. The lower electrode was a water-cooled grounded cathode of diameter 13 centimeters. It was actively water-cooled to get rid of any temperature gradients in the neutral gas. On top of this electrode, we had kept a metallic ring. And along with that, the dust particles, which were monodispersed melamine formaldehyde particles, those were kept right on top of the electrode, covering the inner surface of the electrode. And these are the typical discharge conditions which we used to study these in these experiments. So with that, I will start with observations. So this is the lower electrode, and this is the ring capped on top of the lower electrode, and this is the upper anode. So we saw these two dust clouds which rotate in opposite direction. I'll play this movie in a second. And, or maybe I shall play it just now. So these dust particles are rotating of the metallic ring. And the dust particles are only present in this region or in this region. There are no particles over here. Most of them are located in these dust clouds. And they are rotating in the opposite direction. And we further investigated it, and we found that these dust particles are actually forming a torus where the dust particles are rotating in the colloidal direction. So that is why they were rotating in the opposite direction. And here we were only illuminating the central plane of the dust torus. So these are solid like dust vortices. So these are at a discharge current of 17 milliamps and a pressure of 110 pascals. Now here I'm showing you the evolution of these dust vortices with discharge current at a pressure of 156 Pascal. So we had a dust vortex. So here I'm only showing you half of the torus, or just one plane, one side of the dust torus, like the half plane. So at 20 milliamps, we had a solid looking dust vortex where the dust particles were present at the center and also all the way up to the outer edge. When we increase the discharge current, we observe that the size of the dust cloud increases, and at the same time, the entire dust cloud moves towards the cathode. So the distance from here to the cathode and here, it is less at 25 milliamps. And at the same time, we see less number of particles at the center. When we further increase this discharge current, there are even less number of particles. So these are hollow dust vortices. And the size of the cloud has increased further. And we can also say that the dust density varies during these transitions. Another observation is this, that with an increase in discharge current, the velocity of the dust cloud also increases. Here we do not see a much bigger change, but at 30 milliamps, it is certainly much more than what we have over here. So it is typically 4 centimeters per second, and here it is around 4.5 centimeters per second. But the maximum velocity of these dust particles is around here. And I have used particle image velocimetry to find out the velocities in these planes. For getting these velocities, I used around 1,000 frames. And the velocity is maximum here, but we cannot measure velocity over here because of some limitations of particle image velocimetry here. So now I will, to understand why we saw this transition and why these parameters are changing with changing discharge current, I will talk about the cause of rotation of these dust vortices, dust particles over here. And then we will talk about what could cause the formation of these hollow vortices. So let's start with that. To figure out the cause behind the rotation of these dust particles in the vertical direction, we carried out background plasma measurements using a single Langmuir probe. So here I'm showing you radial density profiles at multiple heights above the cathode surface. So this is at 0.9 centimeters, this is at 1.1 centimeters, and this is at 1.7 centimeters above the cathode surface. So we see a large density gradient in the vertical direction as well as in the radial direction. And in the same way, we have a radial electric field and a vertical electric field. And these gradients coincide with the rotation, with the location of the dust clouds. And these are causing the dust particles to rotate. So basically this density gradient or this density is exerting a force on the dust particles, which is the ion drag force, which is causing these particles to rotate. So I'll show a simple picture where this is our dust cloud, and we have a radial gradient in the ion drag force because of the radial gradient in the density, which is exerting the larger force on one side of the dust cloud and a smaller force on the other side of the dust cloud, which acts as a torque and basically makes the dust cloud rotate. And this electric field keeps the particles, prevents the particles from falling on the surface of the cathode. So in this way, this is the ion drag force, which is making the dust particles to rotate, or I would say the gradient in the ion drag force. But along with this vertical, radial gradient, there is also a vertical gradient. And because of this vertical gradient, and in addition to that, there is a electric field. And the change, yes,
Just
yes.
2 minutes.
Oh, sorry. I will speed up. This is the cause of rotation of these dust particles in this case. So now let's go back to our observations. So we had 3 discharge current settings, 20 milliamps, 25 and 30. So these are the density profiles at these different discharge current values at one particular location, at one particular height. So what we observe here is that with an increase in discharge current, we see an increase in the absolute value of density as well as increase in the gradient. And so that could explain some of the things. So for example, the high density causes smaller sheets. That is why the dust particles move downwards. And these high densities cause higher ion drag forces as well as an increase in its gradient because of a change in, because of an increase in the radial density gradient. So that could cause higher velocities and larger dust cloud sizes. And the cause of the hollowness is could be explained in this way. So we did not have like a lot of data of the potentials. So at different vertical heights. So that can be explained in this way. So we had, so this is the potential radial, a hypothetical radial potential gradient. These are the types which we find in our experiments. So at each and every location, we had a inward directed ion drag force and an outward directed electric force. So the balance of these forces basically gives us a solid dust vortex. But whenever this electric force is higher than the ion drag force, it will cause the dust particles to move away from the center. That will basically create hollow dust vortices. So with that, I will summarize my talk. So I showed you these colloidal dust rotations, and we saw that with an increase in discharge current, the dust particle velocity increases, and as well as its size increases. And with an increase in discharge current, the dust particles, the solid dust particles, become hollow. So yeah, I think that is it. Thank you very much.
Thank you, Manjit. I think there are 3 questions. I'll just read them out. Question answer. Can you put that, show that? Yeah. So what was objective to measure the plasma parameters outside the torus region? I think outside parameters are not playing any role to the vortex motion.
Well,
You
outside,
agree with that? I think that the forces
yes.
are not playing any role in the vortex motion.
Oh, you mean okay, let's go back to here. So yes, whatever
Okay,
is
another question. Vortex are only seen in dust acoustic waves or dust particles, or it is also seen in the electron acoustic or ion acoustic waves.
dust rotations are seen in
Vortex. Vortex are only seen in dust acoustic waves or dust particles, or is it also seen in the electron acoustic or ion acoustic waves?
I don't think that they see vortices over there. They certainly see, so waves are different than vortices, right? Yeah, I don't agree with that.
Manjit.
Yes.
Hello, Manjit.
Yes, I'm listening.
Yeah, Bharat is speaking, Bharat Kakoti. Yeah, so I have only one query on your slide number 10. Yeah, this is. Yeah. If you see for Z, just only for 2.2 centimeter difference, if you see point Z, 1.1 centimeter and 0.9 centimeter, why there is a huge density gradient, but which is not found for like 1.7 and 1.1? What is the main reason?
Oh, okay. So this is basically, so you might have heard about ion bombardment of cathode, right? This ion bombardment basically increases when ions move towards the surface of the cathode. So right next to cathode, the ions are going to hit with very high velocities. And as you move away from cathode, they will, their energies will drop. That is mostly because of the electric field. So ions are accelerated towards the cathode because of the electric field. So that is why you see large densities like towards the cathode surface. There is a big gradient. And we created this radial gradient as well. That is what gave rise to these vortices.
Okay, thank you very much, Manjit. So I think now you can go to sleep there. So thank you very much. We now come to our next speaker, Dr. P. Saikia from Center of Plasma Physics, IPR, Assam, Guwahati. The topic is the electrical asymmetry effect in a multi-frequency geometrically asymmetric capacitively coupled plasma, a study by a nonlinear global model. So we request Dr. Saikia, your time starts now, and we talk for 12 minutes and followed by 3 minutes of questions. Thank you.
Thank you, sir. Thank you, sir. Can you hear me?
We can hear you.
Okay, sir. I'm sharing my screen now.
Yes, go ahead.
Okay. Can I start now?
Yes, you have already finished half a minute.
Okay, sir. Thank you, sir. First of all, I like to thank the organizer of NCRUST for giving me the opportunity to talk in this conference. Today, I'm going to talk about the electrical asymmetry effect in capacitively coupled plasma by a nonlinear global model. And I'm Partho Saikia and from Center of Plasma Physics, Sonapur, Assam. Let me start with this presentation by a brief introduction of capacitive RF discharges. This type of discharges are used for a variety of plasma processing applications.
Your presentation is not visible. Kindly reopen and share.
Okay, now is it visible?
No.
Okay. Is it any problem now?
No, we can see now.
Go ahead.
Okay, thank you. Okay, this kind of plasma are used for a variety of plasma processing application ranging from chip and solar cell manufacturing to the creation of biocompatible surface. In its simplest form, the capacitive RF discharge is driven by applying a RF source to a parallel plate electrode combination. Usually the RF source is applied to the lower plate of this such kind of a parallel plate combination. This is known as the powered electrode, while the upper electrode is grounded and known as the grounded electrode. In most of the application, the chamber is also connected with the ground so that the area of the powered electrode is much lower than the area of the grounded electrode. This kind of discharges are known then geometrically asymmetric reactor, while when the area of the powered electrode will be equal to the area of the grounded electrode, then they are known as the geometrically symmetric CCRF discharges. These are typical parameters of plasma in CCRF discharges. For example, the electron temperature is few eV, while the ion temperature basically at the room temperature. The electron and ion density in the range from 10 to the power 14 to 10 to the power 16 per meter cube, having a degree of ionization between 10 to the power -6 and 10 to the power -4. Different kind of frequency can be used in order to drive discharges ranging from 1 to 100 megahertz. And again, depending on the application, various electrode area, various electrode gap, as well as driving power are used in order to drive this kind of discharges. So here I'm going to talk about the most basic phenomena of single frequency capacitive RF discharge, which is the generation of DC self-biased voltage. Actually, when RF source is applied to the electrode via a blocking capacitor, then there will be a time average voltage drop across the electrode, because in one RF cycle, the current passing through the capacitor will be zero. This current is basically consists of the electron current and the ion current. In the plasma, the ions are much more massive than the electron. Therefore, in order to have equal ion current and the electron current, the electrode should be constantly at a negative potential. So we can define the DC self-biased voltage as time average voltage drop across the powered electrode sheet minus the time average voltage drop across the grounded electrode sheet. And mathematically, the DC self-biased voltage is given by this expression. In this expression, VM1 and VM2 are the maximum voltage at that input RF waveform, and epsilon is the discharge symmetry parameter, which is basically defined as the ratio of the product of ion density in the powered electrode sheet multiplied by square of the electrode sheet at the powered electrode and divided by the ion density at the grounded electrode sheet multiplied by area of the grounded electrode sheet. Now, for a geometrically symmetric reactor, the value of the discharge symmetry parameter is between 0 and 1. And for geometrically symmetric reactor, the value of discharge symmetry parameter is equal to 1. So although the single frequency CCRF discharge has been used for variety of application, there are many limitations of such kind of discharge. One such limitation is that the ion energy and ion flux cannot be independently controlled. As one can see, if we increase the RF voltage amplitude in this figure, there was a gradual increase of both the ion flux as well as the ion energy. So flux and ion energy cannot be independently controlled in single frequency discharge, but variety of plasma processing application demand an independent control of ion flux and ion energy. So in order to achieve this dream, in the last decade, the concept of classical dual frequency discharge have been applied. Such kind of discharge is realized by driving the powered electrode using two RF sources, which are fundamentally very different from each other. In our experiment, we have carried out the experiment by using two RF sources in the combination 2.26 plus 27.12 megahertz. The 2.26 RF source was used as the low frequency, and 27.12 is the high frequency RF source. In one part of the experiment, the low frequency power was fixed at 40 watt and the high frequency power was varied from 10 to 80 watt. And in another set of experiment, the high frequency power was fixed at 40 watt and low frequency power was varied from 10 to 80 watt. The black line here shows the effect of the low frequency power at a fixed high frequency power of 40 watt, and the red line here shows the effect of high frequency power. In the figure 1, I have plotted the value of DC self-bias voltage, which is nothing but the measure of the mean ion energy, and the figure 2, I have plotted the bulk electron density, which is nothing but the measure of the ion flux bombarding the powered electrode. As one can see, with the increase of low frequency power, there is a drastic change of DC self-bias voltage, but the increase of high frequency power, we have not obtained such a rapid change of DC self-bias voltage. On the other hand, by increasing the high frequency power, there was a gradual increase of the bulk electron density, while the low frequency power doesn't have that kind of an effect on the electron density variation. So from these two figures, one can conclude that certain degree of independent control over the ion flux and ion energy can be obtained using classical dual frequency discharge. But the things are not always as good as it sounds. There are many limitations of the classical dual frequency discharges. One of the limitation is the frequency coupling effect, and another is the effect of the secondary electron. Due to the frequency coupling effect, there is a decrease of the bulk electron density with the increase of low frequency power, and due to secondary electron effect, there will be an increase of the bulk electron density at certain pressure with the increase of low frequency power. But in ideal scenario, the low frequency power should not disturb the ion flux or the bulk electron density. It should have only influenced the ion energy. So the situation is not ideal for industrial application. So in order to overcome this limitation, in the last few years, the concept of electrical asymmetry has been developed. In electrical asymmetry, the powered electrode is basically driven by a combination of two frequencies. In such a setup, the high frequency is the first harmonic of the fundamental frequency, and there is a constant but variable phase difference between the low frequency as well as the high frequency. As you can see in this expression, the value of the low frequency is twice the value of the the value of the high frequency is twice the value of the low frequency, and there is a variable but constant phase difference between the low frequency as well as the high frequency. In this figure, I have plotted the difference between the maximum and minimum value of the applied input voltage as a function of the phase angle. As you can see, with the increase of the phase angle, the difference between the VM1 and VM2 also increases. Now, if one remember the value of the DC self-bias voltage, it depends upon in the values of VM1, VM2, and epsilon. So, by changing the value of the phase angle between the driving frequency, one can change the value of the DC self-bias voltage. Also, there is a great advantage of electrical asymmetry effect, because even in the case E is equal to 1, which is the case of geometrically symmetric reactor, and DC self-bias voltage cannot exist in kind of geometrically symmetric reactor. But now with the help of the electrical asymmetry effect, we can create the DC self-bias voltage in such type of a chamber. So one can conclude that with the electrical asymmetry effect, we can convert a geometrically symmetric reactor into electrically asymmetric reactor. Now, in the analytical part, while developing the analytical model of CCRF discharge, the bulk plasma is represented by a series combination of a inductor and a resistor. The resistor basically represents the electron neutral collision, while the electron inertia is represented by inductance having a value LP. In the sheath part of the region, the electron current is represented by a reverse bias diode, while the ion current is represented by a constant ion source, and the powered electrode sheath is represented by a capacitor having a voltage of VSP, while the grounded electrode sheath is represented by a capacitor having a voltage VSG. The capacitor of the matching box is represented by a capacitor having a voltage of VB. Also, in this analytical model, we have assumed an ion matrix sheath approximation, so that the voltage drop across the sheath and the sheath charge shares a quadratic relation. So using all this assumption, we can now write the equation for the change of charge through the powered electrode sheath by equation 1, while the equation 2 represent the change of charge through the grounded electrode sheath. The variation of voltage across the matching capacitor is given by third equation, while the variation of discharge current is given by this fourth equation. Now, one of the major limitations of such analytical model is that this model is not self-consistent. That means we have to take the input parameters of the model from an already existing experimental setup, and once we input those values of the input parameter in the model, it can take out the value of output parameter, such as the sheath charge at each electrode, the DC self-bias voltage, the plasma series resonance effect, and also the output current. The input parameters of the model will be the electron temperature, the applied input RF voltage, the ion density in the powered electrode sheath. This is the time and space average ion density. That's why it's a global model. We have not considered any local variation of ion density. And finally, so as
you have 2 minutes more.
Okay, sir, I can wind up. As I have already told, the input parameters are taken from an experiment by Sunjal, etc., all at different values of geometrical asymmetry. In the first figure, I have plotted the value of DC self-bias voltage at different values of geometrical asymmetries R1, R2, and R3 as a function of phase angle. As one can see, with the increase of phase angle, there is a decrease of the DC self-bias voltage. Also, the increase of the geometrical asymmetry decreases the control over the mean ion energy. On the other hand, with the increase of the number of harmonics like N2, N3, and N4, N2 represent the fundamental frequency and first harmonics, N3 represent the fundamental frequency and its first two harmonics, one can see that the control of the DC self-bias voltage increases with the increase of the number of harmonics. Now, I have already told that output current can be, the RF current can be output of the parameter. Here are the output current obtained at different values of the phase angle. And if we take the first Fourier transform of this output current, one can also obtain the FFT amplitude at a different values of phase angle. And this effect is known as the plasma series resonance effect. And it is one of the main mechanism of stochastic heating in CCRF discharge. So by electrical asymmetry effect, we can also have control over the electron heating in such type of a plasma. So finally, I conclude that thus DC cell bias voltage can be controlled by wide range with the variation of phase angle between the driving frequency. With the increase of geometrical asymmetries, the control is shifted towards the lower value, and we can also have control over the electron heating using such type of a electrical asymmetry effect. This is my publication in physics of plasma, and I would like to thank my team for carrying out the work. And finally, I would like to thank the organizer again for giving me the opportunity to present my work. Thank you.
So, Dr. Saikia, I think there is no. If questions, in that case, I would like to thank Dr. Saikia and his team for this interesting presentation. At this point, before we go to the next speaker, I have a small announcement. This is a mail which has been sent to the presenters of the posters. So it says, you must have read it, but if you haven't, let me tell, because I see on to this presentations right now. So this is for the information to all poster presenters. Large number of participants, it will not be possible to follow the notified paper presentation schedule. The individually examine the posters online, making queries if required to the presenters in the poster web portal. Shortlist a group of posters from the engineering and technology and pure science section separately. And for presentation on the final day, on the basis of which awardee will be announced. So be ready, because your evaluators might have queries to ask from all of you, and then they will shortlist probably. Come to the next presentation, which is by Dr. Sarathi Kundu from IISST Boragaon, speaking on organic thin films. So I request Dr. Kundu to
Yes,
give a presentation for 12 minutes and 3 minutes for questions. Please go ahead. Dr. Kundu.
Yes, sir.
You unmute yourself first. Unmute. Yes, please speak now.
Go to the right bottom corner. There is a slide. Right bottom corner.
But nothing is visible here. Is it showing the problem? I'm not getting. Is it okay now?
click on F5, it will go to full screen mode.
You go to full screen mode, click.
Okay. Is it okay now, sir?
Yeah.
Yes, please go ahead.
Okay, sir.
Last 1 minute.
Okay. Thank you. So first of all, I would like to thank the convener and all the members of this conference attending. So title of my talk is Organic Thin Film, and I am from IISST. So there are different types of organic thin films, Langmuir films, Langmuir logic films, polymeric thin films, and self-assembled monolayers, and also organic films by molecular beam epitaxy. But in my work, I will mainly talk about Langmuir films and Langmuir-Boisjodt films. So first, I will talk about structures and organization of fatty acid monolayer thin film in presence of dissolved ions, and then protein thin film, and then lipid protein mixed film. So organic molecules like or like amphiphilic molecules like stearic acid, lipids, when they are spread on the water surface, they form a monomolecular layer, which is called Langmuir monolayer. And usually on Langmuir trough is used, and when the monolayer is spread on the Langmuir trough, it forms a monolayer-like structure. And this is the most easily achieved two-dimensional system. And if we compress this monolayer, then different phases and phase transitions we obtain. But if we compress the monolayer up to a certain critical point, which is called the collapse point, then it can take different 3D structures, that is structures in the third dimension, that is in the Z direction. And there are different collapse natures depending upon the physicochemical properties of the monolayer. In one case, it can form the constant pressure-like collapse, and their trilayer-like structures are formed. And in another type of collapse, where constant area-like collapse is obtained, that is, collapse occurs at a particular area, and there are multiple layer-like structures are formed. This is called Ries mechanism, and in another case, it is called folding and sliding mechanisms. So there are different structures can generate from this kind of organic monolayers if we compress beyond the critical point. And these type of structures are usually deposited on some solid substrate by Langmuir-Boisjodt method. It is called where a substrate goes from water to air and films are deposited on the solid substrate. And the structures and morphology of these films are obtained from atomic force microscopy and XRR technique. This is AFM and XRR techniques. XRR techniques is actually a X-ray reflectivity method. Here, X-rays are incident on the thin film, and the reflected rays which we obtain, that we need to fit, and then we obtain the average electron density of the film, thin thickness, and interfacial roughness. So in our study, we have used the stearic acid monolayer and used different divalent ions like magnesium, calcium, zinc, cadmium, and barium in the water surface. And we have seen the collapse nature as well as the morphology and outer plane structures of those collapsed films. And it is seen that in case of magnesium and calcium, even after collapse, if we deposit the film at higher surface pH, around 9.5, it forms only a monolayer-like structure, and the morphology is like this. And also this line profile matches with the XRR thickness. Now, but for zinc and cadmium, which we have seen that collapse is like constant area-like collapse, their trilayer-like structure is formed, which is obtained from XRR analysis, and it also matches with the AFM line profiles, and the corresponding morphology are also obtained from AFM. But for barium, although it is like that, but the collapse nature is totally different, and here multilayer-like structures are formed at higher pH, and also matches with the AFM. So this is the model that in case of magnesium and calcium, the monolayer-like collapse is still there, but in presence of zinc and cadmium, it forms trilayer-like structure, whereas for barium, it forms multilayer. So what is the reason? To get the reason, we took the help of FTIR study, and it is known that metal and this carboxylate head group can form three different kind of structures, but in this case, it has formed unidented coordinate-like structures, and in another case, it forms that bidentate chelate-like structures. But in case of unidented chelate, that in the dipole moment is exist both in plane and out of plane direction, whereas for bidentate chelate-like structures, this dipole moment exists only in the z direction. And this collapse nature as well as collapse structures is actually the combination or the effect of the ratio of these two different structures. And it is found that this is when that U by C, that is unidentate by chelate value, is less than 0.66, then it starts to form trilayer as well as multilayer structures. But when it is more than 0.66, it follows the monolayer-like structures. And this is different structures, out of plane structures, which is obtained. It is related with the two-dimensional percolated network-like structures. And so in our collapse, monolayer collapse nature, we found the specific structures, and this is really matching with the two-dimensional percolation model with these collapse behaviors. And this is accepted in Fitzgerald E. And then in the next part, which is protein field, then I will talk about the protein layer field. Here we have used BSA field. Here BSA, you know, BSA is a globular protein, and it has isoelectric point is 4.8. So it means below it is it has net positive charge, and above it has the negative charge, and it has structures like oblate, spheroid-like, ellipsoid-like structures, which has dimension 9 cross 39 cos 39 angstrom cube. And what we have done, we have taken that compression decompression isothermal cycles at different pH, that is far from the isoelectric point, that is at 4 and 8, and one is very close to the isoelectric point of the protein. And it is seen that when it is far from its isoelectric point, it shows it is compression and decompression. It nearly follows, and it comes to its initial point. But in case of when it is very close to the isoelectric point, it shows some irreversibility in the compression decompression isothermal cycle. And this is the optical image obtained from booster angle microscope image, and it is seen that there is no specific pattern. Mostly homogeneous like structure is formed, but when it is more compact, it shows little. It looks little. Bright image. But when it again during decompression, and that is at this point when in the second compression, that is after full compression, this is the initial compression at lower pressure, and it is the maximum pressure at the first compression. But after full decompression, again after second compression, when we have taken, again it nearly follows the first compression like pattern or morphology. And this is the XRR result, and it shows that when we have compressed the film and have taken the and deposited and took the structure, when it is far from its isoelectric point, initially it is monolayer or tilted, very slight tilted monolayer-like structures are present, which is obtained from XRR profiles. But after compression, when it gets the maximum compression on point, that is the 19 milliliters per meter, it shows a tilted-like structure. But and again after decompression, it follows its initial structure. But when it is very close to its isoelectric point, then from the very beginning, it takes these tilted-like structures, but after compression, it takes the bilayer-like structures. But again, when if we decompress the monolayer, and again if we compress the monolayer, this initial structure we don't get. So, and this also matches with the AFM morphology and line profiles. And this is the surface pressure area hysteresis value as obtained, and it is the hysteresis value obtained from XR excess scattering result. And it is seen that when the proteins have its and there is no net charge on the protein surface, that is when protein is basically neutral, it shows this kind of maximum hysteresis value. But before and after, when it has some plus charge or minus charge, and their hysteresis is negligible. And this is the summary of this work, which I have already said, that the hysteresis is, there is no hysteresis when it is little far from its isoelectric point, but hysteresis is present when it is very close to its isoelectric point. And it has accepted in call sub B. Now, I will talk about my last part, that is the lipid protein mixed films. And here we have taken an BSA as a model protein, and lipid, this is DMPA lipid. So we have mixed the films. We have seen the hysteresis behavior of individual lipid and as well as individual protein at below and above its isoelectric point. And when we have mixed these two things and these two components, what we have seen that when it is far from its isoelectric point, that is below its isoelectric point, their hysteresis is very less. But when it is above its isoelectric point, and that is at pH 7, their large hysteresis is there. Now, our motto is why it is so, and what type of structural or morphological modification has occurred in this kind of model membrane like films. So this is the, again, this is the optical image of pure protein. This is during the first compression at lower pressure as well as at high pressure. And again, it is after decompression, again compression at lower pressure after during second compression. And although it is showing this kind of domain-like patterns, but as we have already shown in case of DSA protein, there is no any kind of specific pattern, but it is mostly homogeneous like structures. But if we see the complex, I mean the protein lipid complex films, here you will see this is totally different than the individual component. This is the optical image during first compression at lower pressure, and it is at 40 millinewton per meter at higher pressure. And again we have decompressed the monolayer, and then in the second compression it is like this. And you can see there now that proteins are in between these lipid domains, and this is the XR results. And here you can see that when it is pH 4, here initial lower pressure, higher pressure, and then again the maximum pressure, and then after decompression again it is the lower pressure. These things is nearly where it follows its initial structure. But in case of pH 7, it is not following its initial structure. It means that protein which we have compressed, it actually moves from the lipid lipid tail part, where it is more hydrophobic. When it is moved to its hydrophobic region, after decompression, it cannot come to its initial position, that is near to the lipid head group position when the pH is 7. But when pH is 4, after maximum compression, when decompression occurs, these lipids which actually is lifted from the lipid head group region to lipid tail region, it could come back to its initial position, that is near the lipid head group position. So so it is like that. So now I want to acknowledge my team and also the ISST and DST for funding support. and my students Kaushik, Bijoy, and Rokti for this study. Thank you very much for your kind attention.
Thank you, Dr. Kundu.
Thank you, sir.
So if there is any question, I don't see any question. So we once again thank Dr.
Okay, sir.
Kundu for
Okay, sir.
this
Thank you, sir.
interesting presentation. Thank you. So
Thank
we
you.
request you to disconnect your presentation so that our next presenter, Neetu Borgohain, will present on care nonlinearity induced self-phase modulation in a 3-level semiconductor quantum well system. And Dr. Borgohain is from USTM, Meghalaya. So we request you to give a presentation for the next 12 minutes, which will be followed by 3 minutes if there are any questions. Okay, go ahead.
Thank you so much, sir. A very good afternoon to everyone present here. First of all, I would like to thank the organizers for giving me this opportunity to present my research here. So this topic is car nonlinearity induced self-phase modulation in a 3-level semiconductor quantum well system. I'm from Department of Physics, University of Science and Technology, Meghalaya. The outline of my topic is the introduction, then we'll be discussing about the car nonlinearity, then we'll discuss on self-phase modulation, then
Can you speak a little loudly?
quantum wells.
Can you speak a little
Hello?
loudly? Yeah.
Can you hear me, sir? Am I audible now, sir?
Yes. Yes.
Okay. So
Yes, go ahead.
I'll be, yeah. So there will be mathematical model, then discussing EIT and nonlinearity, then nonlinear coefficients, then car nonlinearity induced is SPM, my topic, then the conclusion and the references. So first to introduce, here I'm going to introduce linear and nonlinear optics. Actually, we divide the timeline of optics research into 2 parts: pre-laser era and post-laser era. In the pre-laser era part, we call it linear optics. Then after the advent of laser, it becomes nonlinear optics. So in the pre-laser era, the fundamental problem regarding the light-matter interaction are very limited, since the field strength available at that time was very small, up to of the order 10 to the 5 volt per meter. So that the small value of field strength was unable to change the system, atomic system, in much better way. So this that is why it is restricted the light matter interaction to some few limited excitations only. The field strength required for the light to affect the atomic or interatomic system is about 10 to the 9 to 10 to the 12 volt per meter, and which was much higher than the conventional sources of light that at the time we had. So thus the polarization of the system was also linear. The expression is linear. So with the advent of laser, the field strength excellently increased, and it now able to affect the interatomic system, and consequently the polarization expression finite terms are added. So here you can see that this is the polarization system, polarization expression, and instead of the only linear part, now we have some few non-linear part also available now in the polarization expression. So thus non-linear terms are now responsible for 2-photon, 3-photon, or multi-photon excitations in the system, and also emission of light of different frequencies than the input one. So due to nonlinear optics, we get a new color out of the monochromatic source. Here you can see this is 1 photon, 2 photon. 2 photon excitations are there, and when emission is we get the emission, then the emitted light frequency become different. So it gives a different color. So from this monochromatic light source, we are getting a different color. So this is how nonlinear optics started. So here I'm to discuss the Kerr nonlinearity. This Kerr effect is a nonlinear optical effect which occurs when light propagates through any nonlinear medium. Say for example, this is a nonlinear medium and this is a pulse, and it's propagating through this medium. So due to this nonlinearity present in this medium, what it will change its refractive indices, because it can be described as a change in refractive index caused by the electric field and being proportional to the square of the electric field strength. The nonlinearity is now is a combination of linear refractive index and the nonlinear part, which is associated with the field strength or the amplitude of this electric field. Now, the power dependence of the refractive index is responsible for Kerr effect. Because of this, the intensity dependent nonlinearity refractive index, there will be a change in the nonlinearity here, change in all the effects here, which will be induced by this nonlinearity. Now, this N2, which is nonlinear refractive index, has a direct relation with this Chi3 or the third order susceptibility. So these two are interrelated. So if we have a nonlinear system, then we have a Chi3 or third order susceptibility, and third order susceptibility is responsible for many interesting nonlinear effects, which are, for example, self-phase modulation, cross-phase modulation, four-wave mixing, etc., etc. And these are basically the primary function of these effects are to produce new or to generate new frequencies. So and also the materials possessing large Kerr nonlinearity can show up these phenomena at very low input power. Now we'll be discussing about what is self-phase modulation. This is an important nonlinear phenomenon that leads to the generation of new frequencies. For example, let us take an optical pulse of this form, and it is presented by this figure. This is the optical pulse, and it has two parts. One is leading edge, one is trailing edge. And this optical pulse is composed of an amplitude term E naught T and phi NL, which is the phase shift, and this is this is a function of E naught T square or intensity square. Then gamma is the nonlinearity, and P naught is the input power, and Z is the distance. So with distance or power or nonlinearity present in the medium, this phase shift will be changing. And as the phase shift will be changing with time, it will be leading us to a frequency chirping. If a frequency chirp will be there, so that will be giving us a new that will be leading us the phase modulation in phase, and that phase modulation will be generating new frequencies. So here in this picture we can see in this leading edge, we can see that this is frequency chirp, this is expression of frequency chirp. So for this leading edge, the chirp is going down, means the frequencies are lower here and frequencies are getting higher here. So low frequency and high frequency are getting in the leading and trailing edge. So there will be a frequency change. So that will be when we see the pulse spectrum, then the Fourier transformation, we can see what are the new frequencies are generated. So this is the structure of the new frequency generated, or the intensity pattern of the self-phase modulation dominated spectral distribution. Here you can see that from one pulse, it become in the output it become composed of several pulses of this form. So this this way, from one pulse, it can produce several pulses at the output. This is because of the cell phase modulation. So why we are taking semiconductor quantum wells? This cell phase modulation is already studied in optical fibers, photonic crystal fibers, and different waveguides. But we have selected the semiconductor quantum wells because first, let me give you the glimpse of semiconductor quantum wells. What are they? They are very thin layered semiconductor structures, and the charge carriers are free to move in 2 dimensions, and motion in the 3rd dimension is restricted.
You have 3 minutes. 3 minutes more for your presentation.
Okay. So directly coming to the advantage why we are taking this semiconductor quantum wells. So they are largely they provide large electric dipole moments, so they possess large non-linearity, and they have flexibility in device design, so they can be easily integrated in other semiconductor devices. So this is the mathematical model that we have adopted. It has been drawn by a molecular beam epitaxy method, and it has 40 couple 40 periods, and the this is gallium arsenide, which is of 92 angstrom dimension, and these are the layers of aluminum indium arsenide, and it has 3 energy states, and these energy states are coupled by the 2 lasers. One is a probe laser, one is control laser. Probe laser is weak and control laser is strong. So by some mathematical tool, we have found out what are the linear and non-linear expressions of susceptibilities. So this is a linear expression of susceptibility. This is non-linear or Kerr susceptibility, and we also have found out what is the nonlinear Schrodinger equation. This nonlinear Schrodinger equation will giving giving us the information how light will be propagating and what are the effect will be there in this during the propagation. So first we come to the imaginary part of first order susceptibility. What it gives? It gives the information about a very beautiful this one effect, which is called electromagnetically induced transparency. Here, initially, when control field is off, then we get a very intense peak of this one absorption. But due to presence of this control field, this intensity peak becomes reduced into divided into 2 parts, producing a transparency window. This is a transparency window where the absorption is almost 0. So in that case, what we get, we have the peak value of this susceptibility or Kerr nonlinearity is of the order 10 to the minus 11. And if we have conventional fiber, then it was 10 to the minus 22. So it is our in semiconductor quantum well, this is becoming much larger than this conventional fibers. So this is again what is gamma. Gamma is nothing but an expression of nonlinearity, and this is responsible for the cell phase modulation, cross phase modulation, modulation instability, or other effects. And this can be found at very low power if we have very high gamma. And this is what is SPM produces. We have removed the dispersion part. We only we only check what are the information that we can get from this nonlinearity. So pulse we employed is a Shek-Hartog pulse of this form. Its duration was 100 femtosecond of full width at half maximum, and peak power chosen is 2 watt, and pump wavelength, it was pumped at 4.116 micron, and the length of the semiconductor quantum well was 2.5 micron, and the nonlinearity was very high. So since nonlinearity was very high, so we get this very beautiful structure of cell-phase modulation dominated spectrum at the output. So these are the slices at different length. This is at input. This is at 1 micron. Where at 1 micron we get a few peaks. At 2 micron, this structure of this output become modulated, and at the output, final output, we get a very nice oscillatory structure with different frequencies embedded. So this numerical study shows that the possibility of SPM-induced pulse broadening at low peak power in semiconductor quantum wells using a large Kerr nonlinearity under EIT. A side hyperbolic pulse of 100 femtosecond duration found at 4.166 micron wavelength with 2 watt peak power, and that generates a broadband spectrum at the end of 2.5 micrometer semiconductor quantum. And it generated spectrum, the generated spectrum was asymmetrical and composed of self-phase modulation dominant oscillations. And this investigation can be proceeded with supercontinuum study by incorporating the dispersion terms. This present investigation may have potential application in the field of optics or optical metrology, spectroscopy, or optical frequency generation, etc. So this is important. So I thank the organizers again and for giving me this opportunity to present. Thank you, sir.
Thank you very much. Thank you, Dr. Borgohain. Let's see if we have any questions. No. Thank you very much for presenting the Kerr cell nonlinearity calculations, simulations. Now, we come to the last presentation before lunch. That's by Dr. Srivastava, who is from CIT, Central Institute of Technology, Kokrajhar. And he will be talking about perpendicular magnetic anisotropy of cobalt and nickel to multi-layers thin film. So I request Dr. Srivastava to come on with your presentation, and we give you 12 minutes, followed by 3 minutes for questions, if any. Thank you. Please go ahead.
Thank you very much, sir. So, good afternoon, everyone. Myself, Dr. Sandeep Srivastava, and I hope that it's audible. I mean, you are able to hear me clearly. Is it, sir?
Absolutely clear, absolutely clean screen.
Okay.
Thank you. Go ahead.
Thank you. Thank you so much, sir. So, I will be speaking on a topic called perpendicular magnetic anisotropy of cobalt-nickel multilayer, and basically the application of these kind of material in storage devices. So the outline of my talk is, first I will briefly introduce the subject about magnetic storage devices, and then I will present few results which we have obtained from our research group on cobalt-nickel multilayer, and then I will end my talk with conclusion. Well, it is very worthwhile to mention that many electronic devices has become a part of our daily life. For example, laptop, mobile, camera, DSLR, so many things. And it's very important to note that for all these electronic devices, we need to have some kind of storage devices. I mean, so-called storage media. And broadly speaking, the storage devices are classified into 3 classes, like magnetic storage devices, flash memory, and optical storage. I think most of you know about optical storage like CD and other things. Of course, it is not being used in that much level, but I would say that magnetic storage devices like hard disk drive and this kind of devices are being used extensively. And I am mainly interested in talking about hard disk drive. So, well, it is very interesting to note that when the very first hard disk drive was introduced in 1956, it had a storage capacity of only 5 megabytes per square inch. But in present time, or as of now, we have hard disk drive which can store 420 gigabyte per square inch. It means that just in the order of size of 1 square inch, we can store 420 gigabyte. And of course, this enhancement of storage density was or became possible just because of the dramatic advancement in the media or so-called material which are used and the recording and writing technology. You can see from this curve, like there was a significant or dramatic advancement in areal density of hard disk drive. And I will say there was an advancement by a factor of 30 to 40 million when since the first drive was introduced long back. And of course, I should mention here that any hard disk drive, it contains three important parts. First part is like media part, also called in simple language material part, and then writing heads and read heads, reading heads. I am interested in talking about the media part, and here I would like to emphasize that in any hard disk drive, the media part is basically made up from the conventional, especially in conventional hard disk drive, they are made up from multi-layers of thin film or magnetic alloys. And there is always a goal that if we can reduce the grain size of these multi-layers, then we can significantly enhance the storage density. And of course, there was a frantic race in industry and as well as in academia to enhance the storage density. And in that way, there was a kind of goal to reduce the grain size. But there is a problem, serious problem with such kind of material called thermal stability issue. If we keep on reducing the size of the grain, so there is a term called thermal stability, which is defined by KUP by KBT, where of course KB is a Boltzmann constant, T is the temperature, which is usually room temperature only. So there are only two parameters, like Ku is called magnetic anisotropy and V is the volume of the grain. So it means that we have already reached to a certain level by reducing the grain size of this material. So there is only one another way. If we can significantly enhance the so-called anisotropy constant, then in that way we can enhance the thermal stability and ratio of thermal stability, and in that way we can enhance the storage density also. So in our present work, basically this is a kind of part of work what we are doing in our research group. So since there is a time limitation, so I decided that I will present just few results. So in present work, we have taken up cobalt nickel multilayers, and it should be mentioned that cobalt nickel multilayers is a widely studied multilayers, and already a lot of work has been done. Here, it should be mentioned that the perpendicular magnetic anisotropy of this cobalt nickel multilayers, they depend, it depends on a lot of influencing parameter like sputtering condition, what substrate is used, in situ annealing of the substrate, underlayer, post annealing. But the thing is, all the previous work, they were focusing the independent influencing parameter. Here, what we have done that we have done a comprehensive and comparative study by preparing the material under different conditions. And now I will present few results. So here we have prepared cobalt nickel multilayers using DC magneton sputtering, and these multilayers were prepared on silicon and glass, and of course they were prepared under various conditions. Like the first condition was we prepared just cobalt nickel multilayer without using any underlayer. Then second condition we prepared with some copper underlayer. Then third condition was we have done in situ annealing of underlayer along with substrate. And then last condition was we prepared material under post annealing. So in that way, our idea was we can have a kind of comparative study, and then we can screen the material which is exhibiting the best property. So of course, before initiating any deposition, we have like first determined the deposition rate of each metal which was used, and of course we check the surface roughness and topography of these material using a technique called 3D optical profilometer. I know that most of the researcher in material science, they use AFM, and 3D optical profilometer is also as good as like AFM. So after preparing these multi-layers of thin film, the first goal was to check what kind of crystalline orientation these materials are going to show. So we used X-ray diffractometer, and from the X-ray diffraction pattern, here I have presented two typical XRD pattern of as prepared and in situ annealed cobalt nickel multilayer. And from the X-ray diffraction pattern, it was observed that these materials were crystallized, or they have a crystalline in the direction of 111 plane. And from the like topography, surface topography, we observed that the edge prepared materials, they exhibit very high surface roughness just because of there was a growth of large isolated bamboo shoot like grains. On the other hand, when these multilayers were in situ annealed, in situ means like substrate and underlayer was annealed, then the surface roughness becomes comparatively smooth. And so indeed there was a drastic change in the surface roughness or the material prepared under different conditions. Then we check the magnetic properties of these multi-layers. The very first parameter, we can see that all these materials exhibit room temperature ferromagnetism, and all these multi-layers which were deposited on glass as well as on silicon, they exhibit perpendicular magnetic anisotropy for the case of edge prepared material with copper underlayer and in situ annealing. However, we observed that when we post anneal the material, in situ post annealing we have done. So in that case, the perpendicular magnetic anisotropy was going to be destroyed. In simple word, perpendicular magnetic anisotropy was vanished. Then we have estimated all the parameters for these multi-layers prepared under various conditions. So from this curve, you can see that the coercivity of edge prepared material was found to be of the order of 150 oersted. However, with copper underlayer, this coercivity was found to increase. Again, it was found to decrease with in situ annealing and post annealing. On the other hand, for saturation magnetization, we can see that there was not a significant change in saturation magnetization, but the maximum value was observed for the case of in situ annealing. Similarly, we checked the squareness also, and it was observed that the best squareness was observed for edge prepared material and in situ annealed multi-layers. On the other hand, it was found to decrease for in situ annealing multi-layers, and again post annealing for post anneal material also the squareness was found to reduce. Now, since in beginning I mentioned that perpendicular magnetic anisotropy constant is one of the very important parameter for multi-layer, and if we know the perpendicular magnetic anisotropy constant, then only we can make use of these multi-layers. So in order to ensure the perpendicular magnetic anisotropy constant and to estimate this constant, we measured initial magnetization curve or so-called wedging curve for all the prepared multi-layers. Here I am showing two typical curves for edge prepared and in situ annealed cobalt nickel multi-layers. And here we can see that for edge prepared materials, the anisotropy constant was found to be just 1.90 10 to the 5 or per centimeter cube. However, with in situ annealing, the magnetic anisotropy was found to enhance significantly, and that is 8.35 to 10 to the power 5 or per centimeter cube. I must mention that this value is relatively considered as higher anisotropic magnetic anisotropy constant value. And so as a conclusion, I can say that we can easily tune various properties of these materials by putting a underlayer or doing in situ annealing or by doing post annealing, and in that way finally we can have a we can screen the best material exhibiting best kind of best perpendicular magnetic anisotropy constant. Well, these are some recent publications which we have published from our research group on this subject. So these publications are we published in last 2 years. And of course, I am very thankful to different funding agency for supporting our research work like DST-SCRB and UGC-DAE CSR, and my collaborators from Belgium, France, IIT Guwahati, IIT Patna, and from Bodo Land University. And this is research team who is working behind the curtain. I will say they are the real member who are working hard and giving a lot of result for the group. So thank you very much. I believe that I have completed my talk within stipulated time. So now time for question.
Thank you very much, Dr. Srivastava. You just overshot 1 minute. So that's very good.
Thank you, sir.
I see. Is there any question? Let's see for you. No.
Sorry, sir. I'm not able to
No,
hear.
we don't have in the chat box or in question answers any questions. So that's a very good work and done at CIT, headed by CIT, I would say, with all collaborators. And thank you very much for giving us this presentation. And
thank you, sir.
With this, I would say that we have come to the end of this session. So we are 5 minutes late than the announced agenda, as I see. So we will be back by 2 o'clock after lunch, 2 o'clock Indian Standard Time. I think that would tell that our next speaker from Europe, so he will be basically looking at his clock as 10:30, 9:30, 4.5 hours. This is summertime. No, 3.5. I think 10:30. Anyway, Mike, you would know that. Thank you.
Hello, Dheeraj. I will be, I'm here. I'll be ready in 1 hour. I am ready.
So what time, what will it be there?
It will be 9:33 here.
9:30, yes, okay.
No,
Right.
sorry, 9:30.
Okay, see you then.
No,
Yeah,
sorry.
do you have
sorry.
breakfast or lunch?
Sorry, Dheeraj.
Okay.
It will be 10:30 here. But it's fine. In 1 hour.
Because this is
Back in 1 hour.
Yes. Yeah.
Can I just check you can hear me okay?
We can hear you perfect.
Okay, great. I just want to make sure the sound is working well. Okay, talk to you soon. Thank you very much. Enjoy your lunch.
Yes. Okay. We meet you after 1 hour. Thank you.
مرحبا، معك غسان عنتر. إن شاء الله كل شيء تمام معكم والعائلة كلها منيحة وما حدا صابه شيء. أنا هلا بالأي بي وحأترك إخراج الأيدي العائلي مع جمانة بالفيزيكس ديبارتمنت. Thank you. Okay.
These floating stars at the end of their lives, we just saw. Two, new stars of the same clouds. Rosetta Nebula. This nebula is a vast cloud of dust and gas, extending over the one covered tires. A third kind of
this is the first ever image of jets above and below it, here shown in blue, thought to be created by incredibly strong magnetic fields. The jets extend out at least 5,000 light years, and one of them appears to be pointing almost straight at us. Relativistic beaming is again the reason we can see the jet coming towards us.
Hello. Yeah. Good afternoon, everybody. I think I should wish Mr. Michael Wells good morning. Am I right? You are in the morning over there. So welcome.
We are in the morning here. Yes, indeed. Thank you very much.
We are in the second session, technical session of NCRUST 2020. We have 3 presentations in this session. 2 invited talks. The first by Dr. Michael Wells. He's from ITER organization, speaking from Paris, France. And the second one is by Dr. Ghassan Antar from Beirut. And the third is the oral presentation. So the first presentation, as I already told you, with Dr. Michael Wells. He is at present, he is the overall head of diagnostics in ITER, that is International Thermonuclear Experimental Reactor in France. He is from Ireland and he is basically an electrical engineer and microelectronics engineer from University College of Cork in Ireland. His basic interest is in optics and lasers. He worked initially with far infrared laser systems. Then he developed a compact high power turnable CO2 wavelength laser, which led to a master's in engineering degree, engineering science. And he did his PhD, which was supported by Euratom, that is European Atomic Energy Community, at Colham Science Center near in Oxfordshire in UK. He is at present, as I already told you, is the overall head of diagnostics at ITER. So over to you. Now we are thankful that you have accepted our invitation to talk, and his title of talk is Building and Controlling a Nuclear Fusion Reactor. That will be a very interesting topic. Dear participants, I think you will be very well informed by Michael Wells. So over to Dr. Michael Wells.
Good. Okay. Good afternoon, everybody. I hope you all had a pleasant lunch and now you're relaxed and happy to listen to me for a short while. So I'm going to talk today about building and controlling a nuclear fusion reactor. Can I just check if everybody can hear me? So just to confirm.
Yes.
Okay, very good. So I'm going to talk today about building and controlling a nuclear fusion reactor. It's interesting to note that previously I worked for your Vice Chancellor, Dr. Bora. So it's a great pleasure to be invited here today. So I'm going to talk about the ITER tokamak. This is a multinational scientific collaboration, and it's involving 35 nations. And one of those nations happens to be India. You'll see the flags of the different countries in the top, and I will come a little bit later to speak a bit more about this. The ITER mission is to demonstrate the scientific and technological feasibility of fusion energy and to get a power output of 10 times more than the power in. So we are trying to create a fusion. I mean, you all know that today in the world, there's a huge problem with electricity. With the generation of power. You have coal generation, which is a real disaster for the CO2. You have solar and wind, which are okay in very limited capacity, but not really a serious answer to our energy needs. We have fission, which works to a certain extent, but is extremely unpopular with the population of the world. And basically we are exploring this option called fusion, and we're building a serious project now to develop this. And I will show you more about this in a moment. Now, this is being built in France. I think you can see there, the site is close to Monaco. And as I said, it's an international collaboration. It's an integrated project. So if I have any project manager type people, you will see that you have to work together with a whole load of countries that don't always politically see eye to eye. So you can see here, for example, you have China, US, RF, and I guess if you listen to the news, you will see every day that there are sort of high-level political battles going on there. But actually in this project, we all work together in a sort of happy big team. And it's basically got 7 major members. Europe has many countries, but we consider it as one entity. So that gives us 7 entities if you look around the circle. And where I am right now is the center of the ITER project, is the coordination platform. And in the end, this project is set up such that we share all the intellectual property of the project, because the people put their money in, roughly 25 billion euros. And in the end, they will have the access to the IP. So the bigger picture, to again give you an idea about these countries, we also have some additional members who are, let's say, partially, they're interested at a lower level. And they also make contributions to the project, such as, for example, Australia are making a small contribution. And we also have a little contribution from Canada. This is a special exercise in cooperation coordination. And we believe it's unique in history. And it gives a great opportunity for each of the countries to even though the project is being built in France, most of the money is being spent in the countries where the money was originated. And more, it's not just the money being spent, the technology being developed, the know-how is being developed in those countries. And this is a huge thing, because you're investing a lot of money in this project. And after this investment, you not only have the project, but you've also got the technological investment, and the companies that build the different parts for this project are now able to do many other things, and they can use the money that they had to build the main parts of this project to set up the infrastructure that they can later then do many other things. And a good example, I'll give you an example in a minute. So it's a big step. I'm going to talk about control, and diagnostics are used in control. Diagnostics are effectively what we use to measure and understand what's going on in ITER. And so far, we have a project. We have projects around the world, and the biggest one of these projects is called JET. And this is actually in the UK. There are other versions in Japan and in America, but this one, let's say I just picked this one. It's got a volume about 80 meters cubed, and it produces a power about 16 megawatts. And ITER has a volume of 830 meters cubed, and it'll produce a power of 500 megawatts. And this, you can see here this picture, and maybe some of you know about fusion and some of you don't, but I'll just give you a very quick tour. Here you can see a little person moving. That just gives you an idea of the size. Also, I want to show you the access points because we're talking about control. And this access point is called a port. And we use these ports to put diagnostics inside, and the diagnostics are used to measure what's going on inside the device. And, you know, diagnostics are used everywhere. If you look in medicine and you go to the hospital, they measure your heart rate using a diagnostic. If you have an MRI scan, they measure the image of the inside your body using this scanner. Well, we have to do similar things. And to get the access to the device, we have what we call ports. And I'm showing you the ports here. Say we have 3 ports. Okay, this device is also an INB. It's a nuclear device because the process that we are using creates neutrons. And these neutrons are actually, they need to be managed. And it uses what's called toroidal field coils. It makes magnetic field. And we have a cryostat because we use superconducted coils, superconducted material. And because of that, it sits inside a cryostat. I'll tell you a little bit more about this in a moment. And just to give you an idea about the size of these coils, this is called a TF coil. And it's about 16 meters tall and 9 meters wide. So this has to be transported to ITER. So it's already a challenge, 360 tons. And if you look at what that really size of, this is the size of a 747 aeroplane, fully laden, to give you an idea. Now the site itself is shown here. This is about 50 hectares inside the fence that I'm showing you here. This is the fence. There's actually about 100 hectares if you include everything, but just inside the fence. And this is the building. This is the main building where all the action takes place. And this building is now complete. And inside here, we will do the fusion work. This is a picture that was just recently released. It's from India. It's the top of the cryostat that I just showed you a minute ago. And this was built by Larsen and Toubro from India. And it comes from a place called Hazira. This is actually too big to ship. This is really huge. It would not fit in any road in Europe, certainly in Europe. So what they've done is they've made it into slices. Imagine a pizza and you divide it into sort of 9 slices and they ship each slice. So you get this bit. And then when it arrives at ITER, the company will send a team of people who will assemble this and weld it all together such that it's ready to be installed in ITER. And so let's go through some of the essentials. So this device is going to be hot. I mean, the center of the sun is hot and this is hot, about 250 million degrees. The energy is contained using a magnetic field because that temperature, you have to find a way to contain it. It carries a large current. It's got a large vacuum chamber, about 800 meters cubed, I told you, and we use deuterium and tritium. It's sitting inside a cryostat because we want to cool the coils, because otherwise we can't put the current through them. There'd be too much ohmic heating. We get high energy neutrons produced in the process. In fact, the neutrons are our friend and our foe. They're our friend because they carry the energy that we want to harness. They're our foe because every time a neutron hits something, it can do things to it. And in order to make things work in ITER, we have to understand very well how these neutrons behave. And we have to guard against them and design our equipment to not be reactive to the neutrons. We have a very large plant infrastructure. I just showed you a 50 hectare site. And it's because we have neutrons, we actually end up with a nuclear facility. And the actual official name for this facility is INB 174 in France. And indeed, in order to be able to measure and control, we have several diagnostics. And that's what I'm going to expand a little bit upon in a moment. And diagnostics work in different ways, actually. As I just told you a minute ago, you measure your heart rate by putting some electric sensor, let's say, on your body. It measures some pulses and then it translates it into a screen. Well, diagnostics for a device like ITER work in a sort of a similar way. So you have the whole spectrum to cover. You can look all across the spectrum from the radio waves to the gamma rays. And with a temperature of 250 million degrees, you have quite a choice of measurements that you can make. And you can see that you will be getting gamma rays. Now, if you only have a temperature of, say, 10,000 degrees, then you will not get the ultraviolet, X-ray, or gamma rays. So in a very, very simple way, if you just had a spectrometer and you just look for the spectrum and you see gamma rays, you know that you're already, you know, you've got a hot device, but that's not accurate enough for what we need. We need more accurate diagnostics. And each diagnostic that we use is able to do different things. This is what we call a magnetic coil. So this is like very standard. You wind a few loops of wire and you look for magnetic field change. This is the standard Lenz's law approach. Here you have a microwave. This is, again, a standard microwave. The policeman, when he tries to catch you for speeding, he points one of those at your car and he measures how fast you're going. Well, we can do the same thing. You have infrared. This measures how hot the surfaces are. So we use cameras to measure generally our thermocouples, but generally cameras because they're faster and they're non-contact. We have the visible, which is interesting as well. We have ultraviolet. And then at the other end of the spectrum, we have neutrons. We look at the neutrons and we look at the gamma rays. And so in ITER, it emits in all regions, and we try to make use of this in order to measure what's going on. We also have what we call passive and active diagnostics. Passive meaning we look and see what's going on. Active means we do something, like send a laser in and see what the effect is. So we've actually got about 50 different diagnostics identified to make measurements, which generate about 100 projects in all. And so and some systems are already completed, and we have many left to go yet in this project. I'll tell you more about the timescale in a minute. And we break our diagnostics into magnetic measurements, neutron measurements, optical measurements, bolometry, spectroscopy, microwave, and what we call operational systems, which makes measurements of the wall. And then, of course, we have to do engineering, because with a big project like this, you can't just, you know, go and wrap a piece of insulation tape around something and hope that it's going to work. It's just absolutely not feasible. You have to do everything at quite a high level. And then, of course, we have other systems which are used in special engineering monitoring. And of course, in order to make this work, we need the world's best engineers and scientists and project expertise, and people who are bright, committed, enthusiastic, because with a project like this is new, many things go wrong. And if you haven't got the intellect and the willpower, you give up very quickly. But actually, we have good people, and this is very important. But we're always looking for good people. So if there are any people who are listening who think this is very important, you know, don't forget. And it's very important to build up this team, because we need the right people. The right people make these projects work. And in actual fact, we follow quite a systematic approach. It cannot be random. With 100 projects I have to manage, I cannot just let people do whatever they want and hope that it'll be okay on the day. That's just not feasible. So we have to initially agree what the requirements are, and we monitor them throughout the process. We manage interfaces. We do concept design, intermediate designs, final designs, manufacturing, testing, factory acceptance, site acceptance, installation, commissioning, and operation. So we have to go through all those steps. And so we come now to a little bit of engineering. I showed you a little bit earlier about a port plug. This is shown here. This is a port plug, and this is the ITER device, and this is how we would introduce them. And the port plug carries many diagnostics. I will not go into them right now, but these are being done by people all over the world. So we have to coordinate this integration with all the different teams, all the different time zones, from the west coast of America to the east coast of India, and to Japan, Korea. So we have many different, we have to worry about time zones quite a lot. And we have to design everything for safety, function, reliability, and maintenance. Some items that we install maybe only cost €1 million or 100,000 euros to make, but it could cost 50 million to get access to them again. And therefore, you cannot just put it in and hope for the best. It doesn't work like that. You have to test, and you have to build redundancy into the system. This is again the port plug, as I showed you earlier. This is now an example of the engineering of the port plugs. You can see this is the size of a person, and this is one of the port plugs. And we have 18 of those port plugs. And so we have to test all this and make sure it's working. This is now moving forward. Now, how do we measure the plasma? So we want to understand the shape, and we want to control it. So we put loops. If you think of your Lenz's law, V equals phi dot, I don't know how you say that in India, but you have a voltage generated when you get a flux change. If you integrate that voltage over time, you get a measure of the flux because you integrate the integrate the voltage, and the phi dot disappears, and then you get a flux. And if you can measure the flux, you can tell about the plasma. And if you make many coils and you do some modeling, you can work out the shape of the plasma. But not only that, we also use magnetic coils, like small loops, and with these, we can put them around the device and we can measure, and with some modeling, we can measure the position of the plasma, and actually not only the position of the plasma, we can use, if you integrate the B field around the loop, you know that this gives you the total current. Integral of B dot L is mu naught I. This is a well-known equation. And so with these measurements, we can make a plasma which fits right inside the vessel, up to the wall within about 20 millimeters. So we have a huge vessel, and with this accurate diagnostics, we can basically fill it to the maximum. We cannot afford to be spending 25 billion in a project and then only half fill the vessel. That would not be acceptable. So we have to optimize the use of this vessel and make sure it's fully utilized. And as you know, volume goes as cube, and therefore, if we are out from the wall by 20%, you get a huge loss in performance. So, but we can do this. And these measurements can be used to control, and we've demonstrated in other devices, and in ITER we will do the same thing. That's our intention. But what other things can we measure? So how many particles per meter cubed do we have inside this device? So we want to know that. And to do that, we use a technology called interferometry. Again, I believe that all of you have probably done this sort of thing in your courses. And we use different lasers, for example. And this tip means toroidal interferometer polarimeter. So polarimetry is when you look at polarization, and interferometer is when you look at the impact of a wave as it goes through a medium. And so we combine the two together to give us a sensitive measurement, very sensitive measurement for phase change. And we also get a measurement on the polarization rotation, which allows us to stabilize we don't end up getting any 2 pi phase changes that we have to worry about. So this covers both. And in this case, we use a 10 micron laser and a 5 micron laser, and a CO2 laser and a quantum cascade laser. And inside the device, we have to put, again, engineering. And because it's a big project, it takes about 50 meters to send the signal in and get the signal back. And this generates its own problems. And if you look here, you can see this is a port plug again. We put some lasers inside and we push them around the vessel. But actually, you can't just point and hope, because you need to think the work. And what we do is this is what ITER would look like in reality. You have here the port, and the vessel would be here. And this is where we are sending the lasers from. And so what we've done is we've set up a mock-up of this in the US, actually in this case, and they've set up an equivalent system. And we have designed software which will simulate ITER. And we have done this, and we can show that, if you can see here, the black and the blue are perfectly overlapping. So we can actually, with our system, make a very good measurement, which in fact is what we are trying to demonstrate. So we've developed this. But not only that, we have to develop a 3-axis control. So we measure where the laser is going inside the machine. We look for the reflections, and we adjust the laser to keep it on target. And this is quite sophisticated technology. But without this active alignment, you lose the signal and the system doesn't work. And we have to keep this stable for hundreds of seconds. And in order to do that, we have to put this into action. Now, I mentioned about neutrons a bit earlier. I'll just mention them again. So neutrons play an important role because, as I said, they're generated in the process. And we detect these using different types of detectors: fission chambers, diamond detectors, and other neutron counters. And I'm just showing you a few pictures here of some neutron detectors. And of course, the neutrons, the amount of neutrons that are produced basically is a measure of the power that our device is producing. And of course, as a diagnostic, you absolutely need to know the power. And this power, and you don't just measure it in one way, you have to have some redundancy, because we need to make sure that we are measuring it correctly. And if one measurement breaks down, the system still works. So here now is an example of installing one of these neutron detectors, which we are actually doing right now. So here on the left, you can see the machine. You can see the build inside the building that I showed you a bit earlier. You can see here there are some people installing our neutron detector on the wall of this building. We have to put this in now because very soon we are putting in the cryostat. And once the cryostat is in, we cannot access this anymore. So it has to be installed early. And so you can see here, this is what's being installed. It's a few meters high, but even if it's a few meters high, it looks actually pretty small compared to the building, but that's okay. We also have electronics and cameras. Now I mentioned again about neutrons. Neutrons pick up, if some of you are engineers or scientists, then you have to be able to face up to these problems. We don't just bury our head in the sand when we have a problem. We have to figure out how to get around it. So when the neutrons are pushing out, or the gammas, we have to ensure that our systems are able to withstand those neutrons. And to do that, we have to design them. And we also have to worry about things like magnetic fields. If you build a DCD, I don't know how many of you know about this, but if you know about transformers, you have a classic two sets of coils and you couple the signals from one to the other. But in most power supplies nowadays, they use DC-DC transformers. These are small, very compact devices. But these devices they use a special material in order to be able to make them compact. But if you have a local magnetic field, which we have on ITER, these devices become what we call saturated. And if they're saturated, then they don't work. And if you put them into ITER, they will be broken in literally minutes. The whole thing will overheat and not work. And so we have to make sure we worry about that. And of course, you have radiation effects on components. So we have to worry about this. And in ITER, we have many, many different components. Just in diagnostics, we have 3,665 amplifiers, 56 cameras, around 2,000 power supplies, and many more diagnostic devices. And these are situated all over the plant, some very close to the tokamak, some much further away. If they're further away, then it's not really much of a problem. If they're very close, it's a problem. And I want to just talk a little bit about INC infrastructure. So we are talking about making measurements, but my talk is about measurements and control. So we make the measurements. So the diagnostic makes the measurement, and the whole strategy is to put the information on this so-called information highway. And this is really a real-time signal exchange. So every time a guy makes a diagnostic, or girl anywhere in the world, they know that they have to put their data on this data highway. Then all the other people who are building systems know that if they need some measurement, it will be available on this data highway. So they take this measurement away. And so there's an interaction between all the systems through this data highway. But we not only have that, we have each diagnostic has software which does the analysis. And then we have a plasma control system. And this control system is looking at every diagnostic and it's making decisions about what to do. And in many cases, we have to do decision making, like 2 out of 3 voting. So which system do we believe? Is there a glitch? What do we do? So in order to solve that, we actually, we have, let's say, sophisticated software that's tested in order to avoid, let's say, the fallout of the system working. It's very important that this system doesn't fall over during operation. And the system is set up in a way that is flexible and easy to maintain. So you see each individual diagnostic is providing its own information onto this highway. And so we've not coupled everything together in such a way that it's impossible for us to manage it. So if we get a new diagnostic, we just say, right, you provide the data on the highway. And then the people who are looking on the highway can look for that diagnostic. So this is how we work. Now the project itself is working on what we call a staged approach. And the first stage, stage 1, is expected to be completed around the end of 2025. There's a lot of information here, but you can see here that this end of 25, we expect to have the first part of the plant fully assembled. All the buildings are complete now, but now we are doing what we call the assembly stage. And if you look on YouTube and look for ITER, about a week or two ago, we had the celebration of the start of the assembly of the equipment in the vessel. And it's actually quite informative if you're interested in this whole topic. And then, of course, after that, we will test all the basic plant, and then we will continue to add the final bits, and then we will proceed to commission, and then gradually we will build up the power until we should get to the maximum performance around 2035. It sounds a long time, but our immediate objective is in 2025, and it's already quite a challenge. So we are trying to make sure we keep that in mind. Now, the team, this is just some of the team, because in actual fact, we have about 10% of the team at the central plant, and 90% of the team are around the world. Now, sometimes we come together. We've got about 500 people working on diagnostics around the world. And we have obviously some people working in the central area. And of course, many of the people who are working around the world come to the central team regularly. Although with the COVID story now, this is a bit messed up. But say typically we've got about 100 people working on the site or interacting with our plant. Now I come to my summary. So we have 500 megawatts of fusion power on the way. We have, it's a large, first of a kind project, and it has many challenges and opportunities. Now, if you're depends how your outlook in life is. Some people like challenges and they want to tackle them. And this, I think, is probably why many of the people who work in ITER are at ITER. And they want to tackle those challenges and solve them and move on to more. And there are absolutely many challenges on ITER. Absolutely many first of a kind parts to this project. You really have to use your brain, work out what's going on, and then figure out what the next step is. It's not like you can look over your shoulder and see what somebody else did. In many cases, nobody has done it before. Now we have, of course, built smaller devices before, but you know, it's not the same sort of problems. We get many new challenges. We have right now, there's a big focus on manufacturing and construction, and that's going to be going on for quite a while yet. Of course, we are doing design, we are doing testing, because we have all phases of, with 100 projects, you can imagine that they are in all phases, from finished to just beginning. So out of the 100, we have, let's say, 10% which are complete. We have about 30% which are in manufacturing. We have about 30% in final design. We have about 5% which have not really been fully launched yet. Very few that haven't been fully launched yet. And we have, as I said a minute ago, we have several diagnostic parts already delivered. I showed you the installation of some of these, and these diagnostics will form the basis of the machine control. And if any of you are interested in this project, you can see here, I've given you the link to our website, www.iter.org. And we enjoy many collaborations with all the countries of ITER, which India is one. Dr. Vora, Professor Vora, will be able to advise you on how to contact ITER. There are many contracts, if you're from a company, with different countries, including India. And in my team, I have, you know, roughly in proportional to the number of people, proportional to the contribution, let's say 1/7 or 1/10, we have about, we have people from all the different nations. There are even some positions. We have also something called ITER Project Associate, where somebody could come and work in the project for a year or two. And this works very well. And we have in my team right now, we have many, like more than 30 people who are enjoying that scheme. And then if you're young, we have various internships and fellowships. They're competitive, but if you're interested, you can compete and you can apply for them. So I think with that, I have 5 seconds remaining. So I think I should say thank you very much. And any questions? I don't hear anybody speaking. Is that because you're not there or you're muted? Hello? Okay, so I see some questions, but I don't actually hear. Maybe the main conference hall is muted. Could you just,
Yeah, okay. The question is, why haven't you used any gas-filled neutron detectors? As my knowledge says, they have higher cross-sections.
Absolutely. In fact, thank you very much. So we do use gas-filled neutron detectors, but actually we actually do use them, okay? But there are 1 or 2 little problems. One is that if you put a gas-filled neutron detector inside the ITER vessel, you have to worry that it's going to leak. And if it leaks in the vessel, which is a vacuum vessel, it could give you a slow leak for many years and cause a big problem for ITER. So we do use them, but we use them with caution. So in order to use them, we have to put a pumping chamber into the detector and have a link outside to the outside world. And if the component leaks, we could suck it out. As I said earlier, if you install something on ITER, it might cost, let's say, 100 million to, well, it costs many millions, many tens of millions to install the wall of ITER. And if your component is behind the wall and you have to take it out, it's a major problem. So we have to make sure it works. The second thing is that diamond detectors, for example, have some spectrum sensitivity. So if you can use a diamond detector, you can actually eliminate some of the low energy neutrons and therefore measure more accurately the neutrons you want to measure. So the question is very good. The answer is we do use them, but we have to use them with caution.
The next question is nuclear fusion reactor more sophisticated and accident prone than nuclear fission reactor? Is the other way around actually. In which case more output power is obtained, that is fusion reactor or fission reactor?
So in the size of a fusion reactor will be set, basically it's all, in the end, it comes down to economics. And so a fusion reactor, to make it effective, is roughly about 1 gigawatt, which is about the same size as a fission reactor. But I have to just tell you one very important thing, that fission works on, you get 2 masses of active component, you put it together and it starts to work, and it's extremely difficult to stop it. And when you do stop it, you have what's called the afterheat. You have these long decaying processes that you cannot stop. And they are usually the cause of many accidents because that lasts for thousands of years and you have to cool the components. This is not a problem in ITER. So in actual fact, for ITER, you can switch it on by effectively a switch and you can switch it off by a switch. So from that perspective, it's much more acceptable to the community. And there also, the other thing is there are no long-lived isotopes. Unfortunately, and I'm actually a big supporter of fission, but the problem is, as I said earlier, it's not well enjoyed by the public because I've been many accidents, and this is not good. Fission can be safe if you manage it correctly, but unfortunately, people don't manage it correctly. They very often take shortcuts, and when they make a shortcut, they make a mistake. And when they make a mistake, it creates a big mess. And you have to avoid that. In a fusion reactor, if you switch it off, it goes off. It's actually quite simple. It's harder to get going initially, but once we've got it going, you're good to go.
Okay, next question is one more query. How you have controlled the activation of neutrons? High dose of neutrons might damage the electronics due to activation. Lastly, how are you making the shielding of the neutrons?
Okay, very good question. So the neutrons are born in the machine. I didn't put in any slides to explain the process because I'm assuming you know that already. If you don't, I apologize. Maybe I can just quickly show here. So there's a picture showing the process. So you have a deuterium and a tritium. You get a helium. You get these are combined together and you get a neutron and a helium. This is a high energy neutron in ITER, about 14 MeV. And this basically, when it will activate many things. So we manage this by, for example, the main activation component in steel is cobalt. And so what we do is when we design the steel, we reduce the amount of cobalt. And if you reduce the amount of cobalt, you reduce the activation. So it makes an easy way to control the machine. And remember now, the input is hydrogen, tritium, and deuterium. And so this is basically gas. The output is helium, which is very clean. So the damage to the electronics, we have to do that carefully. So for example, we have developed in ITER all metal Hall sensors. So many of you probably have heard of a Hall sensor, and normally they are made with silicon. But in ITER, the silicon, if you put a neutron into it, it'll destroy it very quickly. But if you use an all metal Hall sensor, they can tolerate very high numbers of neutrons and no problem. So what I said earlier, you have to put your thinking cap on and you have to think, what are the fundamental principles of what we want to do? Let's say what measurement we want to do. And then you have to think, how would you make that measurement in such a way that the neutrons don't mess up your measurement? And so for the Hall sensors, we use all metal, and this works very well. And so how do we handle the electronics? So for the electronics, for example, for the wires, we use something called mineral insulated cable. And this has got a very low sensitivity to neutrons. And so we don't get any major pickup from the neutrons. So every little step of the way we have to think about. For the electronics, we have two different techniques. One is that we push the electronics as far away as possible. So we take it outside and we shield it. And there's a question about shielding. We use, these neutrons have a 1/E width of about 7 centimeters.
We don't hear you.
And a high energy neutron will
We
go
don't hear
through.
you, Mike.
Sorry?
Okay. We didn't hear you in between.
Okay, I'm so sorry. So the neutrons go through, a high energy neutron in ITER will go through about 7 centimeters of steel, no problem. And in order to shield it, we use about 2 or 3 meters of steel, or sometimes we use concrete. It depends exactly where it is. And so this basically shields the neutrons. Now, in actual fact, most of the neutrons are absorbed in the first 30 centimeters of the wall. And that we put water through that and we can heat that water, and that takes the energy out. And then the further thickness is really to control the amount of activation that goes out, the neutrons that go out because they damage things. So we put about 3 meters of shielding around the device. And when we do that, we get almost nothing on the outside.
Okay, now the next 3 questions. How many cords do you have for the IF interferometer?
We have 5 cords.
Okay, next question. How many planes are you measuring using this interferometer?
Okay, so we measure in both the horizontal plane. If you imagine a fan that goes out horizontally, so we measure across the plasma in different places. And we also have a vertical interferometer, and it's also a fan in the other direction. So imagine one is doing a slice through horizontally across the whole device, and the other is doing a slice across vertically. And so with the 2 things together, we can reconstruct what's going on inside this device. But remember, the interferometer is not the only measurement. Interferometer measures density, but actually also we use a technology called Thomson scattering. I didn't have time to show it today, but Thomson scattering is a point measurement in sort of the same way as a MRI measures the detail inside your brain. Thomson scattering can measure very accurately the density detail. So, but we combine the different diagnostics to be able to finally make the measurements.
last question. What other kinds of interferometers do you use?
Okay, so we use interferometers for different things. We have a device called IVVS, in-vessel viewing system. So we have a system which we send inside the device, and we use an interferometric technique to effectively measure a very high multi-gigabit, pixel picture of the inside of the vessel. And this goes into the vessel in 6 places around the vessel, and it builds up a detailed image. As you know, we have the interferometers that I've just explained to you. We also use some interferometry in other measurements which are used to measure the device itself. I mean, when I'm talking about the device itself, we need to monitor the vacuum vessel for stresses. We need to make sure that we are not breaking the vacuum vessel. We need to make sure we're not breaking the toroidal field coils. So we have something like 5,000 measurements which measure all the different parts of the machine. Now, you might think that's a lot, but every major plant has a lot of sensors that are used to monitor what's going on. This is, for example, an aeroplane, a ship, even a standard factory has many sensors that are used to make measurements. And we also do the same thing. And in order to that, we actually have a system which we call Tokamak Systems Monitoring. And this project basically joins together everything that's going on around the plant, and it ships it all into the control room for the operator to be able to see that we are not smashing the device, because this is a huge device, and you don't know unless you measure it. You don't know that you might be damaging something, so you have to measure it. But remember that this might sound a lot, but this is used also in many other areas. And I think we have to do the same thing in order to protect our investment. We cannot ask all our different nations to provide us 25 billion euros and then just not monitor things and blow everything up in one day. It's not acceptable.
Thank you, Mike. That was exciting.
I have a question.
Yes.
So I was going to ask you about these IR interferometers. Are these double pass or single pass?
Mr. Manjitkar, Mrs. Manjitkar, can you type the question, because we don't have time. The other speaker is waiting at Beirut.
No problem.
Okay.
Thank you.
Okay. Thank you, Mr. Waltz. Dr. Waltz, thank you very much for joining us. And it is a great opportunity in listening to you. May I now welcome Dr. Ghassan Antar. Good afternoon, Dr. Antar.
Good afternoon, can you hear me?
Yeah, we can hear you. So we have amongst us Dr. Professor Ghassan Antar. He is at present a professor at American University of Beirut. He was a visiting scientist prior to that in Max Planck Institute for Plasma Physics in Germany, and also a research scientist in University of California, USA. His areas of interest are neutral fluid dynamics, instabilities and turbulence, sub and supersonic gas dynamics, nonlinear dynamical systems, chaos and fractal theory, plasma dynamics, instabilities, etc. He has a diploma in advanced studies from University of Paris, France, and a PhD from École Polytechnique, France. He is the recipient of NATO scholarship in 1997, and he has many publications in internationally reputed journals and a referee of different scientific journals. So welcome, Professor Antar, and Professor Antar will be speaking on plasma physics from fusion and astrophysics, motivations and challenges. It is over to you, Professor Antar.
Many thanks. Thank you all. Thank you for inviting me. It's a real pleasure and honor to be here giving this presentation, especially after Michael Walsh, who's also the expert. So it's a real pleasure. Now, I do not know really the background of the audience, so consequently, what I would like to do is first introduce what's a plasma in a few slides, and then I'm going to go from one application to another, from material science to lightnings to fusion, as we just heard from ITER, for example, and then following the scale. So we go from small scale to large scales, and at each for each application, I would like just to state some of the challenges and motivations of this work. Okay, so what is a plasma? Well, I think that you guys all know, but just in case, plasma is a fourth state of matter. If we take a solid and we heat it up, then the distance between the atoms become greater than the atom size. When it comes to gas, then the distance between atoms is much greater than the atom size. And then even if you apply even more heat, okay, even higher temperature, as you can see what's shown here, to go from cold to hot, very hot, then in this case, you are able to separate the electrons from the nuclei, and in this case, we have a plasma state. So basically, this process of getting rid of the electrons from the atom is called ionization. And this is basically, I'll just give one simple example of ionization, and that is you have a neutral atom, and then you add energy. Okay, this energy can be mass particle, such as electrons, such as energetic electrons or energetic protons, all right? Or it could also be massless particles, such as photons, for example, when you emit light, okay? And under the condition that the energy that you are adding to the atom is greater.
Excuse me 1 moment. You're presenting the view that you should be looking at. Could you just go to display settings and flick the view? If you go up to the top on the left-hand side, do display settings, because we're seeing 2 slides at a time. Sorry.
Slide. Okay. Just please.
Up to the top to go to display settings and switch the view, top of your screen.
Display show, where show, stop sharing. I'm sorry, but I cannot see the remote control.
It should be under display setting. If you look at the top bar, there's display setting. You click it, and then there should be option to flip it.
Okay, let me just get this.
So we're seeing presenter view right now, I think.
Is it better now? Okay. But
no change.
I see it. Screen. No. What can you see now? Can you see the presentation or both of them? Display setting. Okay, I got it. Duplicate slides, swap, presenter, view, and slide. Okay. Is it better now?
Click it. Click duplicate slide view, it works.
It's working now or no?
I think you haven't clicked it yet. If you click it, then it should fix probably. Where it says swap, yeah, now it works.
Now it works?
Yeah.
Now it is.
It's okay?
Looks good now.
Perfect.
Perfect. All right. So let's continue. So I was saying that ionization is basically when you get rid of one electron from an atom. So basically you're going to have one positive charge ion and one electron. Okay. So basically you have 2 types of particles with different charges. Okay. The opposite process is called recombination. And in this case, an electron is brought back to an ion. So you have an ion plus an electron. And this is a neutral atom, plus it may emit some photons that emit some energy because of the conservation of energy. So how does this thing work? Is that basically if you take this graph here, you have the temperature on the x-axis and the probability on the y-axis, and it's in logarithmic scale. You can see that at higher temperature, you have a higher ionization cross-section and lower recombination cross-section, whereas at lower temperature, it flips. So basically, then you will be more recombining than ionizing. So for example, in this ambient room here, we have much more neutrals, and we rarely have ions because the temperature is so low, and most of the excited atoms basically recombine, and there are no ions or electrons which are free to move. So depending on the temperature, mainly on the temperature of your gas, basically, okay, depending on the temperature, you are able to either ionize more or ionize less in your medium. So this is a general look at the plasma which exists around us. You can see on the x-axis you have the number density, and on the y-axis you have temperatures. And you can see that it goes from, you have the flame, the aurora, around 10 to the 15 per meter cube. You have the neon light, you have the solar corona. We will come back to each of these guys, each of these topics as we go on in this presentation. Okay, then at very high densities and very high temperatures, you have inertial confinement for fusion, and here you have the magnetic confinement where the density is roughly 10 to the 18 with 10 to the 8 degrees Kelvin in terms of temperature. So this is a general outlook of basically the presentation, because we're going to go and try to see what are the various applications and various properties of these media. But for the moment, let's try to just make sure that we understand a few things. So plasma first is an ionized gas in which a certain proportion of electrons are rather free to move and not bounded to the atom or the molecule. The ability of the positive and negative charge to move somewhat independently makes the plasma electrically conductive so that it responds to electromagnetic fields. So basically, if you think of it, first you have a gas. So for a gas, you have the conservation equations of particle, of momentum, and of energy. Now, because this gas can also be ionized, so you have electrons and protons, so you have charges. So the charges create electric field, and charge in motion will create a magnetic field. And now, in order to describe this electric field and magnetic field, you need the Maxwell equations, which are the Gauss law, Faraday's law, and Ampere's law, and Ampere's Maxwell law, which describe this whole set. So consequently, it's quite a complicated set of equations that one need to solve in order to really fully understand the various processes which are occurring in these plasmas. So plasma therefore has a property quite unlike those of solids or liquids, and is considered as a distinct state of matter, and it consists of 99% of the visible universe. So basically, I mean, it's really almost everywhere that you guys see. Now, from a technical, practical point of view, the plasma has a lot of advantages. Here I just selected 3. First one, it's hot. Actually, it's very hot for man-made plasma. Often plasma are not dense. So basically, anytime you need to use something which is extremely hot but low density, plasma can be used for this purpose. The second point, and very important, is manipulation from distance using electric and magnetic field. As I said, since the plasma is made of protons and electrons, now you can use a magnetic field or electric field to make the plasma move to the right, to the top, to the bottom, make it go around, etc., etc., etc. So basically, and this is basically by not touching it yourself. Okay, if you have a magnet or you're able to generate a magnet, as Dr. Walsh was explaining in a tokamak, okay, the simple magnetic field is capable of directing the motion of these electrons and protons in the place where they exist. Finally, naturally, plasma recombine to become neutral atoms, leading to controlling the neutral population. So basically here, you can also, as we will see in a few seconds about plasma chemistry, controlling the neutral population could also be quite important, and to monitor for example, the neutrals in front of a certain metal or certain surface, which is also quite important. So now we're going to start going through various applications. I'll start with plasma chemistry. What you can see here is basically various forms of surfaces as treated by plasmas, okay? And you can imagine that each of these surfaces will have different properties, optical properties, electrical properties. And you're able, and we are able as human beings, we are able to control these by actually controlling the plasma source and controlling the plasma material interaction. So to give you one example, as I said, plasma is used as a chemical reactor, providing the desirable species with other things in process. So the energy fed to electrical discharge is gained by the electron. So here, this part here, which is glowing, contains a lot of free electrons, and now use these free electrons to do various types of interaction with molecules. For example, you can have dissociation. For example, the CF4 molecule, when it interacts with the electron, it produces fluorine and CF3 plus an electron. You can also use, depending also on the energy of the electron, you can use it for attachment or dissociative detachment. As you can see, CF4 plus electron give you CF4 minus, so it attaches to the CF4, and then it will dissociate it to CF3 minus plus F. And then the last reaction, but not least, is the ionization, is that when you have CF4, you're going to have CF3 plus F plus two electrons. So you actually, in these three reactions, you only start with a plasma, which give me the electrons, and a CF4 molecule. But then what do we have? We have F, we have CF3, we have CF3 minus, and we have CF3 plus. And so now we can use this, okay, so that we can control for example, the surface of the plasma properties. And this control is often called etching or deposition. What you see here is an SEM picture of a material which is etched, okay? So basically it was full of the same material, and later on, after plasma etching, it's formed of these nanotubes, okay? And now the properties of this material is really extremely different from where you started, okay? And that's why this is why it's used, why the plasma is used, is to do this etching. So the way the plasma species interact with the sample material defines with the dominating operating process. For example, when using a CF4 plasma, fluorocarbon radicals can generate various layers which can interact with the silicon and thus produce this etching. I have a small movie now that I hope that you would enjoy, okay? And this is how about the etching? What is the visualization of etching? So first you put some layer, okay, on the surface, and then you produce your plasma. That's your plasma, and then the positive ions, for example, the CF4 plus, will interact with the neutral atoms, and they will make it etch. They will make it evaporate. They will be released from the surface, and thus this will make this material. You're able to draw these holes into this material. Of course, where you don't want to make the hole, you will put something which is a photoresist. So basically, it does not interact with the electrons of the plasma, okay, or the ions of the plasma. So this is one topic, and then now here I just summarize for you guys some of the challenges. So of course, better control of the removal or the addition of layers. So now from this you can build microchips. Okay, so we want to control it. The better we control, the better the quality is. Okay, understand the various mechanisms of plasma chemistry, especially with the use of new materials. So now I've shown you one example, but it can be many other examples. Okay, many other molecules that are used, how they interact with the silicon or other materials. All this are research. I think currently there is a huge amount of research in this field for many applications. The third item is more uniform and reproducible coatings. If you want to have this process in a company, you want to have it done all the time in the same way and in a uniform way, so that you don't have a different quality for different chips, for example. Better controlling of the doping elements. So basically, this is for also removal or addition of layers. Better control of the crystalline structure of the coatings. Once again, it really depends what you're looking for. Are you looking for a crystalline structure or amorphous structure? And this depends on the plasma properties that you're using, the plasma temperature that you are using, and the gas that you're using. Better adherence to substrates is very important, and also for fusion related topics, is that when you put a coating on a substrate, okay, you want it to adhere quite well, especially when it's subject to extremely high heat fluxes or high neutron fluxes, as you just heard from Dr. Walsh. So this is one area of application in plasma physics. Now we move at a slightly bigger scale, and that is medical plasmas. Okay, it is quite a very important research field, and what people use is what we call cold atmospheric plasmas. Okay, and this to treat viable tissues. It has become a focus of medical research. Also, plasmas are used for biological decontamination, and also several studies have illustrated the lethality of CAP concerning bacteria or fungi, which could be present on people's skin. And then finally, potential application of CAP in cancer therapy are currently explored by several research groups. The goal is to selectively ablate cancerous cells while the corresponding normal cells remain unaffected. And of course, you can quite easily imagine, since we are able to control the temperature as well as the position, I mean, more or less, of the plasma, then we do hope that these applications are quite promising. So in terms of challenges, we are still, I believe, from my present understanding, is that we are still at the beginning of this type of research. I think that there's a huge room for development, for R&D, both in the fundamental point of view as well as from the applied point of view. So, for example, find adequate plasma parameters that interact with living organisms. So, if you want to kill this living organism, or you don't want to kill it, you want to kill something else. So, it's really a large room for research, better understanding of the plasma living cells interaction, and finally develop the adequate plasma devices that can be used in a medical environment. So basically, this is also a R&D major challenge in developing these medical devices. As you guys know, the medical field has its own set of difficulties and has to be used on human beings. So it's really a huge challenge. Now we go from the cell topic to something slightly bigger, which is basically neon lights. Neon lights, as you guys probably know, there's a plasma inside. We use the simple electricity to generate these lights. So how does this thing work? A fluorescent lamp converts electrical energy into useful light much more efficiently than incandescent lamps. So basically, the idea is to generate light at the wavelength of the eye. So you have the human eye in this graph, which is in dashed line, and you have the radiation, okay, which is in the solid line. And you can see that in this case, indeed, the neon light will emit at the light of the human, where the human eye is sensitive, and consequently, it can be used as light, as you guys can see me now, or you can see around you in your room and the ST conference hall, and so this is a major issue. well, why? Because you might say this is old technology. Well, it's old, yes, but it's used everywhere in the world. So really, one of the challenges is to increase the efficiency of light production. Okay, even a small reduction in the electrical energy which is used is reflected in a huge reduction for consumption. Okay, because it's used everywhere. One can think of better understanding the effects of doping of the rare earth gases, basically to produce more light, which is still a topic of research. Better understanding of the collisional processes and the resulting light properties. Once again, the light properties, you want to emit as much light as in the region where the eye is sensitive. We can also use it to emit light, for example, in the infrared, if you want to use it for other purposes. Better understanding of the excitation of electrons in order to emit more light, and of course, decrease the cost of fabrication. Once again, because these are widely used. They are in all over the world in all institutions as light sources. Now we go from light source, which may be bigger like this, to something which is slightly bigger, but not that bigger, which is called plasma thrusters. So as you can see, this is no longer in action. That's the space shuttle, and what you see here are these small holes. These are thrusters. So basically, what if you want to put an object in orbit, or if you want to travel, say from Earth to Mars, okay, you must develop a thruster, okay, which is capable of producing the thrust that you need to go from one place to another, or to change the position, or the position in terms of rotation, or in terms of position around the Earth, or position between the Earth and another planet. So this is also another research, huge research field. To give you an idea, a simple idea about plasma thrusters, I take the example of Vazimir. Here you have, on the right-hand side, you have a neutral gas. Okay, this neutral gas come in, and you have what we call a helicon source. Basically, it's an antenna. Okay, this antenna it emits. It has some definite frequency. That's my helicon RF generator. Okay, and this is where my plasma is produced. Basically, my neutral gas becomes a plasma. Okay. Now, of course, you have superconducting magnets because you want the plasma to remain moving in one direction, which is axial direction. And then you have what you call an ICH coupler, which basically you apply another frequency to heat up this plasma that you generated. And because the acceleration is proportional not only to the density of the plasma, but also to its temperature, because temperature is going to give you the speed, the sound speed at which it's going to propagate in vacuum. So here also I have a small movie. I hope you guys will like it, about the thrusters and the way it is being built. You see, this is the structure. You have a grid. Okay. This is what you call a discharge chamber. These are ring magnets. And you will see they produce this magnetic field that you see here in white line. And then you have the screen, which is electrode, which, as you will see in a few seconds, that's what you use to accelerate the ions, because you still want to thrust. Okay. So please note that neutrons are green and the protons are in blue. So you start with a neutron, with neutral gas. Okay. And then you put an electron. And then this electron with the neutral gas will produce will ionize it. So I have 2 electrons and 1 proton. And then this proton is then accelerated in this grid. And then we're gonna add an electron so that it becomes neutral as it cools down. As I said, the combination as it cools down, and then so that it can go on and not come back to the accelerator. And so this is what is the presently. Some of the research on space thrusters is going on worldwide. and mainly at NASA and at the European Space Agency. This is just another movie showing you the action, plasma thrust in action. You can see it. This is in live pictures. You can see here you have electrodes as they move in, and to measure the plasma properties as they move from the chamber of where it's produced to the outside, where assuming it is space. Okay, so what are the challenges which come with this type of research? Generation of dense plasmas by better understanding the RF wave plasma coupling. So as I said, you have the RF wave which produce the plasma. So the antenna, the design of the antenna, the frequency of the antenna, all these are extremely important properties which enable us to produce for the same RF power a higher density of plasma. The second point is the acceleration of the plasma particle by modifying the electric field, either imposing or self-generated electric field. This can you know, as the plasma expand, it can self-generate electric field, or you can impose electric field, just as the one that we have just seen a few minutes ago. The third point is develop plasma phasing components that can withstand the plasma energetic ions and have long lifetime of operation. We have seen this box where you have these meshes, okay? And these meshes, that's where the ions are accelerated. So basically, if the ions interact with the mesh, you still want this mesh to last and not be basically sputtered and thus completely eliminated, okay? So here also it's material development for plasmas and for longer lifetime space travel. Heating of the plasma, higher velocities needed to have bigger thrust. So as I said, you have a part which is for generation of the plasma. This is one type of research. And second, okay, I have some type of plasma, and now I want to heat it up. I want to apply a different wave to heat it up, and thus to produce a bigger thrust. Now we move on to bigger scale plasma. And mainly, we'll be talking about, very briefly actually, we're talking about lightning, okay? I think most of us have seen lightning. It's really a very, very beautiful event to see. And here what you see is that much about how and why it forms remain to date unknown and subject to scientific research. Lightning can cause severe, and this is a major application for us, okay? Is that because lightning can cause severe damages to electrical infrastructure and to human beings. Other objectives of lightning study include determining the relationship between the electric characteristic of storms and precipitation, convection, and severe weather. This all lies into the weather forecast. For example, I think that Dr. Walsh will agree with me that, for example, when you work in a fusion reactor such as tokamak, okay, the prediction of storms is extremely important. It could really break the transformers that you're using or other equipment. So I'm not gonna stay long. I just want to show you a few movies where the lightning is imaged with a very fast imaging camera. And you see the propagation, okay, of the plasma, okay, in the atmosphere as it goes from the cloud towards the earth. So, what are the challenges? Better understanding of the physics process occurring in lightning. As I mentioned, up to date, still a lot of questions on this topic. Help in limiting, and the idea is to help limit the damage for lightning on electrical equipment and human beings. And of course, one other question would be, can we store the energy from lightning and to help us produce energy in remote areas, mainly remote areas. Okay, so now we go from lightning to fusion plasmas. Okay, as Dr. Walsh mentioned, if we take deuterium and tritium and you give them enough energy so that they combine, they become one. This one nucleus is extremely unstable, okay, and consequently, instantaneously will break into a helium atom and an energetic neutron. And the idea is that we want to use the energy, this output energy, in order for us to produce energy, or in order for us to understand other processes. Now, fusion, there are 3 types of fusion processes. One is magnetic fusion, magnetic confinement, okay? This is tokamak. I'll come back very shortly, very briefly on it. But this is what Dr. Walsh talked about half an hour ago. And basically, this is using, we produce a magnetic field, okay? And we produce a magnetic field in order for us to control, or as best as we can, the motion of the protons and the electrons in a limited space, okay? So that we can produce energy. The second type is a gravitational confinement, and the third type is inertial confinement. So let's talk a little bit about gravitational confinement. You see, this is our sun, okay? And you see that it has just take off the, it has a spherical shape. This spherical shape is a consequence between of the equilibrium between gravitational forces, which bring the plasma to the center, and the fusion, which is basically temperature, which brings it outside the center, away from the center. And this will cause some kind of an equilibrium. Of course, this equilibrium has a lifetime. So our sun has a lifetime. At some point, it will die, okay, as many other suns in the universe. And but until then, we can still try to study its properties and try to understand how it works and what are its main properties. The second way is by plasma inertial fusion. This is inertial. You can see here, this is a deuterium tritium pellet. It can be also put in this kind of substance so that you can heat it directly, as shown here, or indirectly. The main application for this type of research is mostly for military purposes. You can see this NIF. It's a research facility in the United States. This is inside the chamber. So basically, what's the idea here? The idea is to use lasers. These lasers, they are focused on this small pellet, and it's a huge lasers. So what they would do is they will compress this pellet such that it produces fusion, okay, because of the compression, and once it's produced fusion, then it will blow up basically and release its energy. So this is a plasma energy fusion. Now you have seen the ether, which is a tokamak, and the plasma. Here I would like to show you a movie which is taken on MAST. MAST is a spherical tokamak. It's some type of a tokamak with a major radius of the order of the minor radius. Okay, and what I really like to show this movie because it's really showing how plasma work in reality. Please remember that what you see with your eye, okay, what you see is light. This is the cold plasma. Okay, the hot plasma, you don't see it. It does it with your eye. Okay, it does not emit light at in the visible range. Okay, so you can see the time. So this is the startup of the plasma. You can see this is what you call the inner stack here, and outside it's empty. Okay, and you can see now the plasma is starting to form. Okay, now you can see here that there's a lot of plasma material interaction on the inside here, but as the discharge goes on, then you will see that you will have less light, and so the plasma will be away from the walls, like Dr. Walsh showed that you want to optimize the plasma to occupy the biggest space, but at the same time not to touch any of the material except at the diverter planes. Okay, here are the diverters. This is the X point, bottom X point, top X point, and these are the diverters. As you can see, I hope that you can see my cursor here. This is a diverter here, and here this is what we call the last coast flux surface. Okay, and you can see that there are plasma particles which are going outside the confined zone. This is because of turbulence. Okay, which is driving the particle from inside the plasma to outside the plasma, and consequently limiting our capability or decreasing our confinement energy time And this is the reason, actually, this is one of the main reasons why ITER is built so big, so that the fusion which is done in volume will become greater than the loss of particle which could occur on the surface of the tokamak. And as you can see here, the plasma going away, and then you can here we will be. I will show you a disruption, which is also a third major issue for tokamaks. You can see now in a very short period of time, then the plasma goes away, and you are left with neutrals. And so once again, this goes back to what Dr. Walsh was saying, is that if in fusion plasmas, in tokamaks, if you don't have confinement, you don't have a plasma, and thus you don't have any reaction. So just not there. Unlike a fission reactor, where it's always there and you always need to control it. So what are the challenges? Well, of course, higher density plasmas, if possible. Higher temperature, of course, it's quite needed. Better confinement, as I said, you have two types of events. One is on the microscopic level. So you want to limit these events which are taking the plasma outside the confined zone into the unconfined zone, or where it will interact with the what we call the plasma phasing component. And this is really not good because it produces neutrals, it produces impurities, and would limit the plasma confinement and the plasma properties. On the macroscopic level, disruptions and disruption mitigation. As you saw at the end of the movie, we have what we call the plasma disrupted. This means the life of the plasma ended abruptly. Okay, this ending will cause a huge stresses on all the tokamak in many different areas, and consequently, it's a huge challenge for us for the diffusion in the fusion community. So, and lastly, we also need to continue developing adequate plasma phasing components and understanding its properties as we have deposition or erosion of these properties. So this is in a very brief and introductory fashion, the challenges in fusion devices. Now we're going to go much bigger. So where are we going much bigger? We're going to go to the Earth magnetosphere. So as you guys, I think you know, is that the Earth has its own magnetic field, okay, where you have the South Pole and North Pole of the magnetic field. And basically, because of the existence of this magnetic field, we are really protected by the plasma, which could come from the sun by solar wind. So basically, it is believed and it is understood that because of the magnetic field, life on Earth is protected. Okay, and now it comes with it is that, of course, understanding the plasma and its interaction with the magnetic field of the Earth is of huge importance. Okay, and actually there's a name for that. It's called space weather. Okay, and there's a huge community worldwide which just deal with space weather and try to understand the interaction of the plasma which is coming from the sun, okay, with our ambient magnetic field. And this can be shown in this video here, where you can see this is the Earth, and what you see in these lines, I hope you guys can see it, these are the magnetic field of the Earth, okay, generated by the Earth. Okay, and now, as you will see, there will be a plasma which will come from left to right, okay, and will interact with the plasma with the magnetic field of the Earth. Okay, and you can see that, for example, in this case here, the magnetic field of the Earth is highly depleted. What it means highly depleted, this means that if it is totally depleted, then you would have radiation which comes directly from the sun to the Earth, and this is extremely damaging. And it will cause extreme events, as some of them have been detected previously in the past. And as you can see here, there are many interactions. This is from a different point of view, and you can see that now there's a plasma wind will come in, and will interact with the Earth magnetic field. And this interaction is extremely important for the life on Earth in general. Okay, so what are the challenges? Understanding the various processes occurring in space plasmas is still a huge area of research. Better understanding of magnetic connection. Magnetic connection, by the way, is also observed and detected in fusion plasmas, but also quite well, it's very important in space plasmas. Assess the role of turbulence and nonlinear processes in reconduction, and predict the flux of plasma and electromagnetic waves arriving to Earth's surface. And that's what usually people call it space weather, because not only want to understand, but also want to predict, especially that we have artificial satellites who are looking at the sun and its activities and try to see if we can predict whether our magnetic field can resist or not, and what to do in either cases. Okay, so this is now we're gonna go into, so one of the consequences of the interaction of the solar wind with the Earth magnetic field is what we call the aurora borealis, or the northern lights. Okay, what you can see here are the northern lights, which are detected basically in the around the North Pole. And furthermore, these aurora borealis, they do not exist only on Earth. This is on Jupiter. You can see that this light in this region here, which is, there's light coming out of it. It results from the interaction of the plasma wind with the Jupiter magnetic field. So now we go even at a bigger scale, which is the sun. Of course, the sun is a complex, extremely complex medium. Okay, and I'm just giving you one of the mysteries of the plasma around the sun is the temperature in the solar corona. You can see on this graph here, the corona is really outside, if you could say, outside the sun. However, if you plot the density and the temperature, okay, of the plasma in this far region, one can imagine that if you have a source, okay, a source of plasma, the further you are away from the source, the lesser is the density because it will expand, and also lesser is the temperature because it will cool down, because there is no a priori, there is no additional sources. Okay, so basically, it is a very active research field in the astrophysics community. Okay, and the idea is to try to understand where does this heating come from? What is the source of this heating? One of the sources of heating is what we call magnetic connection. Why? Because the sun, it has a magnetic field. Okay, and now if we can convert the magnetic energy into thermal energy, then one can imagine then we can indeed heat up this region which is far from the sun surface. Okay, so here also the research which is done in astrophysics or in tokamak, for example, they come together and this reconnection process plays an immense role is believed to play an immense role in the heating of the solar corona and the plasma in the solar corona. And so, of course, if you have more heating in the solar corona, then as the plasma propagates towards Earth, it's higher temperature, and thus it's much more damaging. It will do much more higher amount of damages. So now we go even much bigger scale. We go from a sun scale to an interstellar medium or dusty plasmas. So in this case here, what I would like to discuss quite briefly are the interstellar medium. For example, here I will focus on nebulas. Okay. For example, you have 3 types of nebulas. Okay. One is what we call the reflection nebula. So what you see here, the light coming from this nebula is reflection from the source. Okay. The second type of so this is a plasma. Okay. Interacting, moving, changing. Okay. And you can also have another type of, it's an emitting nebula. This is the Rosetta Nebula, where you can see now here, you have plasma not reflecting the light, but emitting light, okay? And this emission of light is really because of the interaction between neutrals and hot plasmas, and this giving us this really beautiful, beautiful picture. And finally, there are really what we call dark nebulas, which you don't see. The gas is so dense, okay, that it will absorb the light and will not emit it. I believe many of you have seen what's called the Horsehead Nebula, was shown here, and you see that this is basically, it's like a dark spot in space, and this, of course, all these depend on the density and temperature of the plasmas that, or the gas that you are that exists in space. Okay. Finally, my final stage will come to black holes. I just show you a quick picture of this, the latest picture of a black hole, and you can tell me where is the plasma. Well, what you see with your eye is a plasma. Okay, what you see with your naked eye is what we call the accretion disk. So basically, a black hole, as most of you probably know, is really a collapse of a star. Okay, consequently, all this gravitational, all the mass will be concentrated in a very small amount of space. And this concentration will change the space around it, okay, and will lead to a modification of the plasma or the neutrons even, which are around the space. So this is what you can see here.
The region shows where plasma is coming towards us. And since it's traveling near the speed of light, it appears brighter when coming towards us and dimmer when going away. This is called relativistic beaming.
Yes, this is what I wanted to show you. These are, there's a lot of research, which is laboratory research or observational research, try to understand the accretion disks around the black holes, okay? And consequently, also, they will try to understand the jets which are coming out of these black holes. So I don't know how much time do I have. I'm done, I think. So these are the jets, what you can see. What's my main message? I mean, I hope that I hope I covered what I promised. And so my main message as a conclusion is that research on plasmas extend in scales over a huge amount of scales. You can go from a nanoscale for plasma processing to a micron scale for medical plasmas, to centimeter scale in thrusters, for plasma thrusters, to kilometer scale for lightnings, to tens of kilometers, hundreds of kilometers in the ionospheres, and then to really huge amount of distances as we talk about accretion disks and nebulas. One interesting component, which will go back to what Dr. Walsh presented, is fusion. Now, fusion, let's say even if we talk about just magnetically confined fusion, which is in tokamak, really the plasma properties, okay, they extend from a, let's say, a micron size to meter size, okay? So you can see that the challenges in fusion are immense, because if you want to resolve all the scales, then this is extremely costly and extremely difficult, okay? But my, what I wanted to show here are the various challenges in some of the fields that I selected, okay? I hope that you have a good idea about them if you have not have that already, okay? What I would like to add with one interesting issue, and that is all these processes, okay, they obey to the same equations. So we have the same set of equations, okay, from a physics point of view, okay, which are used and applied to describe all these variational phenomena. And this is what I find extremely interesting and extremely challenging, okay, and extremely beautiful, of course, because I hope that you agree with me that most of what you guys so has some aesthetic into it, which is, I think, non-negligible. Thank you for your attention, and I look forward to answering your questions.
Thank you, Professor. I think I have got a couple of questions. The first question is from Nilanjan Bujarboroa. Dr. Antar, for plasma chemical reaction, which of the principle is more feasible, PECFD or magnetron sputtering?
Sputtering, yes. I mean, the answer to this question is really not about feasibility, okay? It's not about feasibility. It's really about adequate tool to be used, okay, for the specific process that you want to use, that you want to obtain, okay? So, for example, if you want to sputter some material, you might well use magnetron sputtering. If you want to coat some material, you might use PECVD. So it really depends on the material that you are using and on the coating that you want to do it. Okay. So and there are many other types of coatings and sputtering that are used worldwide, not just these two.
So thank you. Another question from Kamal Talukder. How could cold plasma is different from, I think it should be cold fusion? Hot plasma.
Cold fusion is a myth.
I think
it doesn't exist. Cold plasma is a plasma which could basically could not be extremely high temperature. So it's everything is relative. Okay. If you see in this graph here. So at first, let me just make sure that I answer. So cold fusion doesn't exist. I think it's a myth. It's a story. Okay, it's something that you see it in movies. Okay, the reason is that if you want to make fusion, okay, you must overcome the electrostatic repulsion between nuclei. Okay, and if you calculate the energy that you need to apply to overcome this repulsion, you'll find it's huge. It's huge. This means that you must heat up your nuclei, okay, to this amount of energy. For example, there's another cross section for fusion, so that fusion can take place. For example, in today's tokamaks, okay, you have high temperatures, okay, but it's not enough. It's still yet not enough to have a fusion reactor. And this is the main reason why we are building ITER. Okay, ITER is being built because we want to test this really extremely high temperatures where fusion reactions occur relatively abundantly, okay, and not scarcely. And this fusion reactions, what is thought is that it will act as a heating source from inside the plasma. Okay, so there's no such thing as cold fusion. Cold plasma, yes, you have. For example, if you take the aurora, okay, or flames or interstellar space, this is actually relatively cold. But once again, it's all a relative temperature. Okay, if you compare 10,000 degrees Kelvin to 10 to the power 8, it's relatively cold. Okay. So, and you have also room temperature plasmas. Basically, your temperature is cold, so you have recombination, but you are generating your plasma all the time. Okay, so this is why you're able to keep it up. Yeah, keep it up. I hope I answered this question.
I think that gentleman has corrected his question. It was how cold plasma is different from hot plasma.
It's temperature, very easily, very simply. If you look at the y-axis in this graph, okay, you can see that it goes from 100 degrees Kelvin to 10 to the power 8 degrees Kelvin. So this is what we call cold plasma, and that's what we call hot plasma.
Okay, one more last question. How does fusion takes place in lower densities as per the scale you have mentioned?
Okay. Fusion the main component for fusion is temperature, okay? Because once again, you have two protons. Let me go back to this side here. Okay, you have a deuterium nucleus and a tritium nucleus. One, you have one proton. Either in the two cases, you have two protons. And so basically, you want to overcome this repulsion because you have 1 plus 1 plus, they repel each other, and you want them to fuse, so you want them to come together, okay? So the main component is temperature. Now, so this is about fusion. Now, if you want to use this energy, so this produces energy, okay? So assume that you overcome it, okay? In order to overcome this repulsion force, you, as a human being, we supplied energy, okay? So we have supplied this amount of energy, but we want to take energy, okay? So in order to take energy out of, the energy that we take to be greater than the energy that we put, okay, the biggest amount of fusion reactions that occur, the more energy I have. So this is where the density comes to play. So what really determines the fusion reaction of two nuclei is the temperature, okay? Now, but if you want to use this energy to produce electricity, then you must have a large amount of fusion reactions such that you produce a large amount or a huge amount of electrical energy, okay? So these are two different things. So the density is used for, let's say, quantity, and the temperature is for quality, if I can put it in these words. You want to produce more, you have to put more fusion reactions, okay? But for each fusion reaction, you must overcome the electrostatic repulsion force between two nuclei.
So thank you, Professor Hunter. It was a very nice and educative and informative presentation. And we express our thankfulness and gratitude to you from Assam Science and Technology University and the NCRUST team. Yeah, Professor Bora wants to say something.
No, this is to all our foreign speakers, our gratitude in terms of the memento. We cannot give you right now, but we shall be mailing to you along with the book of abstracts, a memento, and a small piece of cloth, which is given to the people as a mark of respect. We shall mail that in a parcel to all of you, including Tripathi, Mike Walsh, and Professor Antar, everybody. We will mail it to you through speed post. So please accept it as if it is in person. Okay, Mike, you heard it.
Thank you very much. We really appreciate it.
Yes, thank you very much for everything, for this organization. Thank you. I think it's quite hard to organize this thing in online. So thank you.
So thank you very much, Professor Wells and Professor Hunter. Now we have another presentation, as in oral presentation 6 on the NCRUST 2020 by Tamen Thapa Sarkar. This is from Electronics and Electrical Engineering Department of IIT Guwahati, Indian Institute of Technology, Guwahati. He will speak on sliding mode control approach to increase robustness and stability in maximum power point tracking of solar PV system. Are you there, Mr. Thapa Sarkar?
Yes, sir. Yes, sir. I'm there.
Yes. You have exactly 12 minutes for presentation, and that will be followed by 3 minutes of question and answer. So we will get a warning 1 minute before end of 12 minutes. So please go ahead, Mr. Sarkar.
Sir, is my slide visible?
Not yet. There is a message that Tamen Sarkar has started screen sharing, but we haven't yet seen. Yes, now it is there. Okay, again it's gone. It was coming, but it vanished again. It will come. Just have you started?
Yes, sir. Yes, sir. I have started.
Just wait. You don't do anything because it takes some time. There's a time lag.
Okay, sir.
It hasn't yet come, but it will come, I think. Yes, there's a message. Just that you don't do anything, it will come. I'll tell you when it comes.
Okay, sir.
Just wait a few seconds. You can start talking. Just initial things.
Okay. Good afternoon, everyone. I am Kamantapa Sarkar, Research Scholar at Guwahati, and my co-author is Bhaskar Jyoti Das, Assistant Manager of Assam Power Distribution Company Limited.
Now it has come.
First of all, I would like to thank
You put it in slideshow mode. It is normal mode. It is coming. You put it in slideshow mode. Full screen.
Yeah, I have already put, sir, in slideshow
Okay,
mode.
it will come. Okay, it will come. Yes, it has come. Open. Now you can go ahead. Full blast. Yes.
First of all, I'd like to thank the organizing committee of the National Conference on Recent Advances of Science and Technology 2020 for organizing this virtual mode. The topic for presentation is sliding mode approach to robust and stability in maximum power point tracking of
Speak little
PV
loudly.
system.
Speak little loudly. Yeah.
The topic is sliding mode control approach to increase robustness and stability in maximum power point tracking of solar photovoltaic system. As we all know that the population of the world is increasing day by day, and so the energy demand. So the conventional fossil fuels are the basic need of energy in this day.
Sarkar, your slides are not there.
I'm trying, sir, once more.
Hello, sir, can you see the screen now?
Yes, switch over to your mobile. Yes, you can go ahead. Talk.
The solar energy, radiant energy and heat from sun that is harnessed using range of evolving technologies. It is an important source of renewable energy, and these technologies are broadly classified as solar and passive solar. Active solar technologies includes the use of photovoltaic systems, concentrated solar power, electricity production includes sunlight can be converted to electricity either directly using photovoltaic or indirectly using concentrated solar power. That is CSP. CSP uses an or mirror and tracking systems to focus clear sunlight into a small beam. PV system converts it into electric current using the photoelectric effect. These are the pictures of solar concentrator and solar photovoltaic which I have used. Now the next picture is of the cell, the basic unit of the solar PV array. The cells concentrate to form the module, modules connected in series and parallel form the array. It is the main system or structure for mounting the PV arrays or modules. Power conditioning equipment that converts the DC electricity to the proper form and magnitude required by an alternating current, and storage devices such as batteries are required for storing PV generated electricity during cloudy days. Next, the maximum power point tracking. It is basically the main algorithm which is essential to generate the maximum power from the PV cell. As we all know that the solar power is variable in nature. Wind, but it is therefore important to maintain optimal power flow of the solar PV system for maximum efficiency. Maximum power point tracking plays an important role in this regard. So for maximum power point tracking, there are several techniques involved, like perturbation observation method, which is PNO. In this paper, we have used both the perturbation PNO method and the sliding mode control method a comparative performance analysis for of PV system. The block diagram for the MPPT control has been shown in the next figure, in which it shows the PV model is connected to the DC boost converter and then to the load through the MPPT controlling technique. This MPPT controlling technique receives the input from the PV module and it does its controlling algorithm to produce the sufficient duty ratio which is required. Now coming to the modeling.
Mr. Sarkar, can you hear me?
Yes, sir.
Yeah, you have 5 more minutes.
Okay. Consists of the eco circuit of the PV cell, which the ideal PV cell and series and the systems. This is the DC-DC boost converter modeling, which is the main circuit for providing the boosting the input voltage. Now, this was the input from the PV voltage and process give. Now the MPPT controlling technique includes two PNO and the sliding mode control. So first I'll be explaining about observation control technique. It works on the MPP PV of Kyocera. And then the PV and current, then it measures the power. That the duty ratio results and discussion part simulated simulating, and we have studied the first the irradiance variation and then
Mr. Sarkar, actually there is no point in, because it is totally, your voice is totally broken, your slides are not, can you come to the concluding slide and finish your presentation? Yeah, it is better because there is no point.
In the conclusion, we can see that both the MPPT algorithm provides design provides efficient results. Both PNO MPPT controlling technique and the SMC MPPT controlling technique could successfully attain the maximum power irrespective of the different weather conditions. PNO MPPT controlling technique, however, suffers during rapid irradiation change and temperature change. It shows larger oscillations and takes a longer time to settle. Sliding mode control, on the other hand, is robust to both irradiation and temperature changes. It also provides tracking and near total rejection of the disturbance. Now, as the SMAT control we have designed is robust and it attains the settling very fast compared to the PNO algorithm, but it has some scattering. We have done some modification, but it has which can be removed in the future works. Also, modified perturbed observe MPPT technique could also be for attaining maximum power at a faster rate and also accurately. These are the references that I've used.
Okay, thank you, Mr. Sarkar. That was no doubt a very important topic, but unfortunately, because of your internet connection or lack of
connection is very lagging, sir.
Anyway, it is sometimes we'll hear from you in some other occasions about that, and including your future walks probably. I don't see any question in the question box. So that was the last presentation in this technical session 2. Yeah, Professor Dheeraj Bora, our Vice Chancellor, wants to speak to you regarding tomorrow's program. Professor Bora.
This is mainly to our participants for tomorrow. Tomorrow we have some very exciting works to be reported. I would request our participants to be in full swing like today to enjoy the flavor of these various different activities which you will be seeing right from the challenges we have for nuclear industry, for nuclear fission. Basically, you will hear from a very, very senior person. Then along with that, you will hear something from the Indian Space Research Organization. Some of our satellites which are being launched, they also have diagnostics on board. So you will see some very interesting results. Along with that, we will even talk about the environment, horticulture. Not only that, even the smart water management, which we need badly in our state. So I request all of you tomorrow morning to be in full force and of course in the best spirit. So today I think we end. Oh, there is an announcement from the organizer's side. I have been asked to tell you. I see right now we have participants which are close to 110, 115. It is fluctuating in the afternoon. Now I have been told that to bag a poster award, you must have an attendance of how much? More than 80%. So please, our participants, I'm sure all of you have posters in the portal. So please be serious about it. And then if you are expecting to bag one of the prizes, then you please bear with us, stay for 80% of the attendance next 2 days. Otherwise, even if you have the best poster, they may not give you the prize. So please remember that. And thank you. Stay safe here in India and abroad. Thank you very much.
So thank you, sir. So that is the end of today's technical session 2, and we will see you tomorrow, once again, at 10 o'clock, I think. Yeah, tomorrow at 10 o'clock and Indian Standard Time, yes, IST. So thank you very much. Today, actually, we are almost in time in almost all the stages. So thank you for maintaining the time. I thank all the organizers and all the participants for maintaining the time. Thank you very much.